The ASSHEE International Workshop was formulated in 2019 by NIT Agartala through an international collaboration with Russia, Finland, and Italy. It achieved an overwhelming success from the students, young scientists, engineers, and professionals, not only in Asiatic countries, Asian countries, and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy, and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise, and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering, and seismic hazard mitigation. NIT Agartala recommends you to join ASSHEE 2020 for a wholesome experience in the field of advanced seismology, seismic hazards, and earthquake engineering.
Hello, good morning everyone.
Morning.
Hello everyone. Good morning.
Hi.
Good evening to you, sir. Chimori, sir. Good evening.
Hello.
Yeah, welcome to the day 3 of ASSHEE 2020. Let's start our first technical session of the day. Today we have with us Professor James Jim Maury. He is currently working as professor in Disaster Prevention Research Institute, Kyoto University. He also worked as research seismologist in USGS and then as USGS Southern California regional coordinator and scientist in charge USGS for the term of 1992 to 1998. He worked as a seismologist USGS and also in volcano crisis assistance team. Today, sir will be delivering lecture on seismological aspects of Great 2011 Tohoku, Japan earthquake. I request Dr. Seema Ghosh ma'am to chair the session. Over to you, ma'am.
Thank you, Pooja. Sir, please start your lecture, sir.
Okay, let's see. Okay, can you see that slide?
Not yet. Not yet, Jim.
Okay. Still you can't see it?
Not yet.
Not yet, sir. You need to share your screen, sir.
Try again.
Yeah.
Yes, sir.
Yes.
Now it's visible.
Yes.
Okay, well, thank you for inviting me to talk to you. I'm very honored for the invitation. And today I'm going to talk about the Tohoku earthquake of 2011. It's been almost 10 years, just a few months. It'll be 10 years to the earthquake. And obviously it's a very important earthquake. It's by far the largest earthquake Japan has ever had, and Japan has had many, many earthquakes. So it's a very important event. Many scientific and societal and engineering topics that we've learned from it. And it's hard to really summarize it, but I've chosen 4 topics I'd like to talk to you about today. So the first is a general seismological background. The second is the slip on the fault, which caused a very large tsunami. The third one is the strong motion, the shaking. And then I'll end up talking about some sort of relevant silent issues that came up because of the earthquake. Okay, so this is Japan, tectonic figure of it. And Japan actually has sort of 3 tectonic plates in the area. And so the islands sit on the Eurasian plate, but the Pacific plate is being subducted under Northeast Japan, and the Philippine Sea plate is being subducted under Western Japan. And so the Tohoku earthquake happened here, along the Japan Trench, where the Pacific plate is being subducted underneath the Eurasian plate. It was very big. It was magnitude 9.1. The size of the fault was roughly about 400 by 200 kilometers. These orange dots are the aftershocks, the larger aftershocks, and they pretty much show the area that ruptured during this great earthquake. There were lots of casualties, approximately 18,000 were killed. And the damage from the tsunami, not from the shaking. It was actually a very significant economic crisis, and it's always very hard to estimate very well what the damage is from earthquakes, but generally the number is around 30 trillion Japanese yen, and that's about 20 trillion Indian rupee, and that's about 5% of the 2010 Japan GDP. So many people are killed, very hard economic results, and so it was really just a huge event for the country. Before the earthquake, there have been many earthquakes, other earthquakes in this area, the Tohoku earthquake, the Tohoku region, and a very good historical record. And in about 400 years, we've seen 13 magnitude 7s and 5 magnitude 8s. And when you see this many earthquakes, seismologists actually began to get confident that they understood what was happening here. After you see earthquakes repeat, after you see many earthquakes, you think you can understand what's happening here. And so prior to the Tohoku earthquake, there was a very detailed probabilistic map or probabilistic study that was done for this area.
Please excuse me, sir. So your slides are not changing, sir. It's constant. The slides are not changing.
Oh, is that right? Which slide are you seeing?
So it's in the front page itself, the cover page.
Is that right? Let's try again.
Yeah, yes, sir. Now it is visible.
Oh, it was visible. Okay. Let's see.
Yes, sir.
So the slides are changing now?
Yeah, it's changing now.
Okay. Let me just back up a little bit then. This shows the aftershocks. And so that shows where the earthquake happened, the rupture area, which was about 400 by 200 kilometers. And I said many people were killed, and economically it was a very big event. So this is what people expected to happen in this area prior to the 2011 earthquake. We saw many earthquakes, and we thought we understood all these little segments. And so specific probabilities were given. So for example, this area here off of Miyagi, they said there was a 90% chance of a magnitude 7.5 in the next 30 years, because magnitude 7 earthquakes happen here fairly often. Off of Fukushima, they said it was a very small probability, maybe 7% in 30 years, because there were not very many large earthquakes. So anyways, people thought they understood very well this segment of the Japan Trench and how often and how large earthquakes would happen. But what happened was, instead of having lots of segments and different earthquakes, the whole area broke in one giant 9.1 earthquake. And so that really, in a sense, discouraged people. I mean, they thought they understood what was happening in this area, but all of their forecasts for the coming large earthquakes turned out to be not correct. So I think this is one of the most important lessons, and that is, even with 400 years of earthquake history in an area that has very active earthquake activity, it still is not long enough to accurately estimate the earthquake hazards. You probably need 1,000 years or several thousand years to be able to say that you understand what's going to happen from the past history. And so this was a very kind of tragic lesson. People thought they knew what was going to happen, but it turned out that there just wasn't enough history. And people have gone back and looked, and they think they found a previous earthquake about 1,000 or 1,100 years ago about this size. But of course, there was not very much information historically for that event. Okay, let's talk a little bit about seismology. When we study earthquakes in seismology, we always want to put a size on them, a number. Magnitude is the most common way, but seismologists like to use the seismic moment. The seismic moment is a more physical estimate of how big or the size of an earthquake. And the seismic moment is calculated by the shear modulus, the area of the fault, and the amount the fault slips. The shear modulus is a rock property. And so that doesn't really change too much earthquake to earthquake. It changes a little bit for shallow earthquakes and deep earthquakes, but not a lot, maybe 20 or 30%. So this number is fairly constant for all earthquakes. Obviously, the big difference is the area. Big earthquakes are big because they cover a lot of area, and small earthquakes are small. And to some extent, the slip also. The large earthquakes tend to slip more. The fault moves farther for the bigger earthquakes. So anyway, seismologists like to think about the size or the physical dimensions of an earthquake in terms of this seismic moment. So here's a summary of some of the largest earthquakes we've ever seen. And so the size of this, the rectangles show the area of the fault. And down here, these numbers are the moment times 10 to the 27th 9 centimeters. And then the bottom number is MW, which is the moment, which is converted into a magnitude, because most people are sort of more used to seeing numbers between 6, 7, and 8 to see the estimates of an earthquake. Anyways, big earthquakes are big. The largest earthquake we've ever seen is the 1960 Chile earthquake. And so it ruptured about 1,000-kilometer long fault that was maybe 400 or 500 kilometers wide. So this was just a huge area that broke during this earthquake. The Tohoku earthquake is probably about the 4th largest earthquake that we've seen. It's interesting that the 2004 Sumatra, the Andaman Sumatra earthquake, is almost exactly the same size as the Tohoku earthquake. But the Sumatra earthquake was much longer and a little bit more narrow than the Tohoku earthquake. So the Sumatra earthquake was actually even longer than the Chile earthquake, we think. It was about 1,200 kilometers long, whereas Tohoku was about only 400 or 500 kilometers long. The other thing I mentioned is that the seismic moment incorporates the slip. And it turns out the Tohoku earthquake had a very large average slip on the fault. So that's another reason, even though the fault area is not as large as some of these other ones, the total seismic moment is still quite large. And we'll come back to that because it turns out the amount of slip is very important for determining the size of the tsunami. Just for comparison, here's some other smaller earthquakes. The 1906 San Francisco earthquake in the US was a very long, narrow fault because it was a crustal earthquake. The 2015 Nepal earthquake, that was about 160 or 170 kilometers long and maybe about 100 kilometers wide. The Gujarat earthquake was about 60 or 70 kilometers by 60 or 70 kilometers. So obviously Gujarat also was a large earthquake for India, but on a global scale, it's very small compared to some of these other really giant earthquakes that we've seen before. Okay, so I mentioned the slip was very important in Tohoku. It really slipped a lot. How much did it slip? Well, for example, here's some measurements that were done on the ocean floor before and after the earthquake, and it moved about 15 meters here, close to the epicenter. It moved about 24 meters. So that's a very large distance for a fault to move. There's been many fault models for this earthquake, probably more than any other earthquake in the past. And people have used teleseismic seismic waves. They've used strong motion records. They've used geodetic records. They've used tsunami. So there's many different fault models for this earthquake. And there's different colors and different arrows, and they look kind of different. But actually, if you look at it, they're quite similar in that this is the area that slipped, the area of the fault, and almost all the models have this especially very large area of slip to the east of the epicenter, out close to the Japan Trench. So all of these models have these red bullseyes or these bright colored ones in about the same place on the eastern edge. And depending on the model, the amount of slip there is generally from about 30 to 60 meters. So again, really a very large slip that occurred on this eastern or the shallow uptive edge of the fault. And as it turns out, this slip of over 50 meters is the largest slip we've ever recorded for a modern earthquake. In the last, maybe 50 years, 60 years of seismic data and geodetic instruments, we've never seen 50 meters of slip before. Typically, magnitude 8s have maybe 10 meters of slip, or very large ones, maybe 20 meters. But this 50-meter slip was really a big surprise when this happened. And as I mentioned before, the size of the fault movement, the slip, is directly proportional to how big a tsunami is generated. And so here's just a photo of the tsunami as it's getting a little bit close to shore. And so in this diagram, this is the subducting Pacific plate going underneath the Eurasian plate. This is the fault. And so this fault slips. And what happens in the earthquake is this upper plate is slowly bent downwards over 100 years, 200 years, 1,000 years. And in the earthquake, it suddenly snaps back, and that displaces the water and causes the tsunami. So here's the same picture. So if there's a large amount of slip on this shallow part, on the place close to the Japan Trench, then that will make the tsunami bigger. And another thing is, this part of the fault is in deep water. And because it's in deep water, when this fault moves, there's a lot more volume of water that's displaced, and the tsunami is larger. So if the big fault movement had been on the shallow area, then only this much water would be displaced, and so the tsunami would not be as large. But since the fault movement occurred in deep water, we have all of this depth of water, this large volume of water that gets displaced, and so when the tsunami moves towards shore, it is much bigger, it's much larger. And so those two reasons the large slip on the shallow part and the fault in deep water are the reasons that the tsunami was so large for this particular earthquake. How large? So here's many measurements of the tsunami height all along the coast of eastern Japan. And can you see? This is 10 meters, this is 20 meters, this is 30 meters. The highest run-up heights were over 40 meters. That's very high. If you can imagine what even 10 meters is, 20 or 30 meters is really a very high wave, a very, very deep amount of water, very large amount of water that's coming on shore. And this is over, so this is 200 kilometers. So over a coastline of maybe 400 or 500 kilometers, there were tsunamis of 10 or 20 meters. So it's not just one small area that had large tsunami, but almost 500 kilometers of coastline had these very large tsunamis of 10, 20, or even 30 or 40 meters. This graph actually shows two different kinds of measurements. The red ones are inundation height, and the blue ones are run-up height. And there's a little bit of difference between that. So if this is the average sea level, then as the tsunami comes on shore, you can measure it. You can measure it with some tide gauges or instrument. And so that height gives you the height of the tsunami, the inundation height. If you're on land someplace and you can see the tsunami, or you can see how far the wave came up, you can also measure it. And you have to, of course, add in the actual height of the land above sea level. And so that's what's called the inundation height of the tsunami. As it turns out, for very large tsunamis, they have some energy. And so the energy actually can have the wave wash up even higher than the actual height above sea level. And so that's what's called run-up height. So run-up heights are always higher than inundation height. So this is sort of the momentum of the wave as it comes on shore. So the run-up heights, the blue ones are run-up heights, and the red ones are the inundation height. So the height above sea level that the wave was at. Now here's a good example of, you can easily see that the water came up to this level here. So all the panels on the veranda, and if you could see, the windows are broken for the first 3 stories here. And above that, all these panels are still in place. So the tsunami came up to about this height here, which is about 10 meters. And I can't remember what the height is above sea level, but that would give you a very good estimate of the inundation height. So 10 meters is about 3 stories. So 10 meters was just a small part. There were many places with 20 or 30 meters of tsunami height. Lots of places in Japan have these seawalls or sea gates that they move to try to protect the areas from the large tsunamis. And a lot of these were closed, but unfortunately for this particular event, the tsunami was much larger than expected. Most of these walls or gates that were put in place are on the order of about 10 meters. And so if it had been a magnitude 8 or even 8.2 or 8.3, probably this would have been enough. And that was the size of tsunamis that most people expected for the maximum size earthquake at that time. Here's a famous photo of the tsunami coming over this seawall here. So this is that wall. And at the time of tsunami, obviously the wall was not high enough, and the water just came in over the top of this seawall. And in some places, the walls were actually broken by the tsunami. So, so the result of the tsunami was just much larger than people had expected. People had not expected a magnitude 9 with 50 meters of slip to happen here. Why didn't they expect it? They didn't expect it because historically they had never seen an event that size. And so that just comes back to what I said before, that even 400 years is not enough to sort of see the whole spectrum of events. Here's the place of the highest run-up, and it was over 40 meters, and you can see the wave just took down the trees and the vegetation, and so the water came up, and again, this is run-up, not inundation height, but the wave came up to 40 meters above sea level at this particular place. Okay, tsunami. So the take-home message from tsunami was simply it was much bigger than expected. It was much bigger because the earthquake was much bigger. And this particular earthquake had very large slip on the shallow part of the fault. And that's what caused the tsunami. It's the largest amount of slip that we've seen for a modern earthquake, about 50 meters. And a very large area was affected by the tsunami. Maybe 400 or 500 kilometers of coastline had tsunamis from 10 to 40 meters. So it was just a huge event, and it was just a devastating phenomenon to see all this water come on shore and do all the damage that it did. Okay, let's talk about the earthquake shaking a little bit. This is a teleseismic back projection model. I don't have time to explain everything about this, but what you're seeing is the results of using earthquake waves all around the globe to estimate the high frequency energy. So the energy for maybe about 1 to 5 seconds that was caused by the earthquake. And so this is a movie of the time evolution of this high frequency energy. And let's wait for it to start again. So here's the epicenter, the hypocenter, and 10 seconds, it's sort of spread over this area. 25 seconds, it's moving to the west towards the shore. And after 50 or 60 seconds, it begins to move to the southwest and sort of down the whole length of the fault. And so the whole earthquake takes about, about 150 or 180 seconds, so 2 or 3 minutes for the earthquake to happen. And as you can see, most of this high energy, the high amplitude, high frequency waves come from the area to the west of the epicenter, on the landward side. And this is very different from what we saw before about the large slip and the tsunami, that the largest slip, the 50-meter slip, is actually on the eastern side. So the amount that the fault moved the largest, or the largest amount of fault motion, was on the shallow eastern side, but the areas that produced the high frequency shaking were more on the western side. And so this is something we see, not always, but we do see occasionally from very large earthquakes, that the areas that had the largest amount of slip are not necessarily areas that produce the strongest shaking. So the areas that have the largest slip produce the tsunami, because this just is proportional to how much the fault slips. But the area that produces the shaking of the earthquake, the 1 to 5 second waves, are due to more small scale features, are due to the rupture pattern, are due to the inhomogeneities, and many more of the smaller details. And so where the fault slipped the largest is not necessarily where the strong shaking that causes the shaking damage occurs. And it shook very hard. Here's some acceleration records for this earthquake. And this is acceleration. And So the highest was 2,900 gal. So this is almost 3G. 1G is 1,000 gals. And so this station here also had over 2G. All of these other stations had over 1G of acceleration. So these are very, very severe ground motions. And unless a building is very strong, this will cause a lot of damage. The other rather frightening thing is the shaking lasted for quite a while. It lasted for maybe 120, 130 seconds, so over 2 minutes. So if you were there, probably that 2 minutes felt like a very long time that the strong shaking occurred. So it shook very hard for a very long time, as recorded by these strong motion stations. Here's a spatial map of the shaking. So here's the peak acceleration, the peak velocity, and again, the red is over 1G. And so all this area, again, maybe a coastline of 500 or 600 kilometers was shaken close to 1G. And basically it was felt over almost the entire area of Honshu. Tokyo is about here. And it had maybe about 100 centimeters per second, about 100 gals of acceleration, which is still pretty strong. A couple days ago, Professor Gupta said that there was no deaths in Tokyo. And that's true, because the shaking was strong, but not very, very strong. It was very, very strong up in the Tohoku area near Sendai and some of these places up here. This is peak velocity. And actually, recently, many engineers say that velocity is a better measure of the ground motions that cause building damage than acceleration. People before used to think that the force, the acceleration, was the key factor, but more recently, velocity may be more important for determining damage. And again, these are very severe velocities, over 100, 200 centimeters per second over a very large area. So it shook very hard over a very large area. And again, the population of this area is well, it's tens of millions of people. So there's really many, many people in this area of very intense shaking. The damage was not zero, of course, but it was actually surprisingly light. I mean, there were buildings that came down, but for example, the deaths from collapsed buildings and landslides was only 4% of the total number of deaths. And, you know, several hundred people were killed, and it's hard to say that's a good thing, but it's rather encouraging that there were so few deaths. Again, you know, there's tens of millions of people living in this area of very hard shaking. So the fact that less than 1,000 people were killed by the shaking, by building collapse, I think is a real tribute to the Japanese engineering. And that's the reason that generally, especially in Northeast Japan, the building standards are quite good. The building standards are quite good because they've had many earthquakes. Particularly in 1978, there was a very severe earthquake in the Tohoku area, and probably that earthquake kind of took out a lot of the weak buildings at that time. And so as they're being rebuilt, they're built much stronger, and so that really helps with the building. So people were killed, but the numbers are relatively small compared to the total population of the area. And again, that's good. That's due to the very good building standards of these areas for the construction. Okay, so for the strong ground motion, the area that generated the strong shaking is different from the area of large slip that caused the tsunami. And there was very intensive shaking, but the building damage was not huge. Of course, there were buildings that collapsed and there were some deaths, but it was relatively small, and you can really credit the engineering standards in Japan for that reason. Okay, let's talk a little bit about some societal issues or some of the consequences to people that we have. And for tsunami, of course, you want to have a good tsunami warning. And one of the important things, of course, for tsunami warning is how fast does the tsunami travel? And so usually at this point in this lecture, I ask everybody, do they think the tsunami is traveling at 40, 80 kilometers, like the speed of a car, or 200 to 300 kilometers an hour, which is the bullet train, or maybe 500 to 900 kilometers, which is the speed of a jet airliner? Unfortunately, I can't see what your answers are, but just take a second to think, well, how would you answer this question about how fast a tsunami travels? And when I've asked different groups, actually, almost about the same number of people choose these different values. So there doesn't seem to be one predominant answer. That there's a whole range of people that choose how fast a tsunami travels when the wave is coming towards you. Actually, it turns out this is kind of a trick question. And the reason is that the tsunami speed, the tsunami speed depends on the water depth. And so in the deep ocean, at say 4,000 meters of water depth, the velocity is about 700 kilometers per hour, so a jet airliner. Whereas if the water depth is only 10 meters, it's traveling much slower, about 35, 36 kilometers, which is the speed of the car. So in the open ocean, the tsunami has a very long wavelength, a very small height, and is moving very fast. And as it comes closer to shore, as it gets the shallower water, the wavelength gets narrower, and the height becomes higher, and the speed becomes slower. So this really controls, the water depth really controls in a simple way the speed and the height. So for example, very often, not very often, but there have been several cases of large tsunamis from South America or North America that have done damage in Japan. So they've traveled across the whole Pacific Ocean and hit Japan. And so when they're traveling across the ocean, they're traveling very fast. They're traveling at the speed of about a jet airliner. And as they get closer to shore, it gets slower and slower. So if you can see the tsunami, maybe you can see several kilometers out in the ocean, and you can see it coming, it's probably traveling at maybe 30 to 50 kilometers an hour. So if you are in a car or a bicycle, you probably have a good chance of getting away or getting far away from the coast if you see the tsunami coming. One other thing is, I said in deep water, the height is actually very small. And actually many times you can't see it in the deep water. And that's the reason that if you get a tsunami warning, if tsunami warnings go out for ports, local fishermen will take their boats out to deep water. Because if they're in deep water, the effect is very small compared to the shallow water on close to shore. So anyways, for tsunami warning, the tsunami is probably traveling anywhere from maybe 30 to 100 kilometers an hour, depending on what the water depth is from the earthquake to coming on shore. Okay, so here's just the equation. It's actually a very simple equation. It's gravity times the water depth, and you get the square root. So for 2,000 meters of water, it's about 504 kilometers per hour. For 10 meters, it's 35 kilometers per hour. So it's actually not super fast. So if the tsunami is coming from a place far offshore, then you have a good chance for getting warnings out and for evacuating people. So what happened during Tohoku? So JMA actually has a very good elaborate system for giving out tsunami warnings. The earthquake happened at 1443, and so JMA broadcast a tsunami warning in 3 minutes. So very fast. The magnitude was a little small. It was about magnitude 8, but they got the initial warning out in about 3 minutes. And then they gave updates every 15 or 20 minutes later as they saw that there were bigger tsunamis. As I mentioned before, the tsunami is actually coming from pretty far offshore, the shallow area. And so that's about 200 kilometers offshore. So you actually have quite a bit of time. So the closest place the big tsunami arrived about 1518, so about half an hour. So even the closest place, they had about a half an hour before the big tsunami came. Of course, there were some small waves ahead of time, but the damaging tsunami took about half an hour. And these other places had maybe up to an hour afterwards. So there was actually quite a bit of time for the tsunami warning that went out and for people to get away. So one of the biggest issues, one of the biggest societal problems is why were so many people killed? If everybody had dropped everything they were doing and immediately got in their car or even just run from where they were, there would have been very few deaths because there was quite a bit of time from when the tsunami warning was issued until the actual tsunami came. And so this is actually have been studied by a lot of different people, and there's lots of complications and reasons. Some of the reasons that I've heard that make the most sense is that one, about 3 days before this huge earthquake, there was a foreshock, about a magnitude 7.4, 7.5 foreshock, and a tsunami warning was broadcast for that event. And a tsunami came, but it was only maybe 10 or 20 centimeters. It was very small. So just 3 days before this huge event, tsunami warning was broadcast with a very small tsunami. And so some people might have thought that, well, this is just like that one a few days before, and so we really don't have to worry about a big tsunami coming. Another issue that I've heard a lot of people mention that they think is the main reason is that even though the tsunami warnings were given on TV and radio, the newscasters were not very excited. I mean, they're trained to be very sort of not excited and with a straight face to report the news and not to be emotional. And many sociologists have said that was not the right thing to do, that they should have been more, urgent or more excited and just telling people to get away from the coast as fast as they could, that this was not a small thing. And so sort of the calm demeanor of the newscasters, they said, also might have contributed to people just not dropping everything and running as fast as they could from the shore. Anyways, there's many studies about this and a lot of different reasons people give for why the people didn't immediately just try to run away from the tsunami. And it's certainly not from lack of information. In the Tohoku area, even all the children are taught about tsunamis in schools, and it's probably one of the best areas in the world prepared for earthquakes and tsunamis. But somehow the real message didn't get across for many people. So like I said, the technical part, the warning, the JMA got the warning out very well, only 3 minutes after the earthquake. It was a little bit small, but there were updates that came later that said the bigger waves were coming. And so the technological aspects of the warning worked very well. The parts that didn't work was sort of the education and the training of people to react correctly and to react very quickly to these kind of warnings. Okay, I think I'll finish up and talk a little bit about the nuclear power plant problem, because you've probably heard a lot about that. This earthquake actually affected 4 different nuclear power plants along the east coast of Japan, but only one, Fukushima Daiichi, was the one that had the problems, the one that had the meltdown and the explosions and the big problem. The other 4 were not did not have the meltdown, and so didn't have the big problems. And again, the reason for the problems at Fukushima Daiichi was the tsunami. There was a wall, about a 12-meter wall, but the tsunami came in over the wall. And what happened was that the backup power supplies for this nuclear power plant were on the ocean side of the nuclear power plant. And so when the tsunami came over the wall, it destroyed the backup power plants, the backup generators. So actually, the nuclear power plants survived the very strong shaking. So even that one that's close to the epicenter that was shaken very hard, the actual shaking didn't damage any of the power plants. They were all designed to withstand the shaking levels that occurred. Even though it shook very, very hard, there was no structural damage to the plants that we could see from the shaking. So what happened at Fukushima Daiichi is the tsunami came over the wall and destroyed the backup generators, the backup power generators. And so, of course, the power goes out after the big earthquake. But because the backup generators were destroyed, there was no emergency power for the reactor cooling systems. And so that was the real problem. Other nuclear power plants closer to the earthquake survived because they could restore their power after the power was cut off. Some of these, the backup generators, were in a different place, not close to the coast. Others, they kind of brought in some cables to restore the power. So anyways, at the other places, they were able to restore power. And so that's the reason the other plants survived. So anyways, the bottom line is it was not the shaking. You know, everyone was really worried about the shaking before the earthquake and wondering if the designs were good. But the engineering plans for the earthquake shaking were worked very well. The problem was the tsunami. And so, you know, it should have been recognized, it should have been in the plan, but it just wasn't sort of thought through the whole scenario for this particular event. So the bottom line, not the bottom line, but the reason that this nuclear power plant had the meltdown is not because of the earthquake shaking, but because the tsunami came in and destroyed the backup power generators. So if that had been thought out a little bit better, then there wouldn't have been this disaster at Fukushima Daiichi. Okay, well, I think pretty much stop there and just maybe, again, go over the points that I'd like you to take home with you. One, even in a very active place like Northeast Japan, where there's many earthquakes, many large earthquakes, 400 years of history is still not enough to adequately characterize the earthquake hazards. That in order to see the magnitude 9, you probably need several thousand years of seismic records. And because of that, the tsunami was much larger than expected. And the tsunami was very large because of the large slip on the shallow part of the fault. The fault was shallow, it was in deep water, and so it caused just these huge waves that were from 10 to 40 meters height that really caused the damage for this event. The fault region of the large slip that caused tsunami is different from the areas that generate the strong shaking. So if you're worried about tsunami hazards, it's different from worrying about the strong shaking hazards, at least when you're talking about the sources. So the sources of the strong earthquake shaking are different from the sources of the large tsunami for this particular earthquake. The shaking was very hard, was very harsh, was very large, but the damage to building was relatively small. Of course, it wasn't zero, and there were still several hundred people were killed. But I think, in a sense, that's a fairly optimistic number considering the tens of millions of people living in the area, and that can be attributed to the good engineering practices in Japan. And finally, the meltdown at the nuclear power plant Fukushima Daiichi was caused not from the earthquake shaking, but because the tsunami destroyed the backup generators. And so if that had been thought out a little bit better, then that particular disaster would not have occurred. Okay, so I think I'll stop there, and if people have any questions, I'd be happy to try to answer them. Thank you.
Thank you, sir, for your nice, elaborate, and smooth presentation. It's very smooth presentation. I think each and every participant enjoyed that presentation.
Thank you very much.
Now, question answer, sir. Sir, there is one question. Can earthquake and tsunami be known in advance with the available scientific tools?
Do you mean earthquake prediction? Is that what they're talking about? Or we can give long-term probabilistic estimates pretty well, which means in 100 years we can give good estimates of magnitude 7s and 8s if we have a good record. And if we know the probabilities, then we can know how big the tsunamis are from sort of doing calculations. So the answer is, over a long term, maybe scales of 10s or 20 years, we can give a good idea of how often or where a big earthquake would occur and the size of tsunamis. Unfortunately, for this particular one, we were very surprised that this was so huge, so we were wrong about this one.
So there is another question. Do you think shaking would be different place for continental earthquake as we see in Tohoku?
Yes. For example, the Nepal earthquake, the strongest shaking was on the northern edge of the earthquake fault, sort of the down dip area. But the biggest slip was a little bit more to the shallow part, more underneath the plain. So even for continental earthquakes, there's often difference between the areas of strong shaking and large slip.
May I ask a question?
Sure.
This is concerning the history. You said that it's about 400 years of known history. But I have seen some publications that there were also traces of paleo tsunami, which were showing much higher splashing traces of splashing water than even was observed during this earthquake. Can you comment on that? Is it true, or it was just speculations?
No, it's definitely true. And it's because after this earthquake, they went back and looked more carefully, and they found what they call the Jogan earthquake in 860 something. And they found tsunami deposits that were about the same size or maybe larger. So from that, they said that there probably was also a magnitude 9 in the year about 800. So yeah, those kind of old geologic tsunami deposit studies are very important for trying to estimate how often and how big tsunamis occur. Unfortunately, that was done in hindsight. It was only after that they found that information.
Also, Sumala sir shared one feeling, sir? Similar thing happened during 1905 Kangra earthquake. Sumala sir is sharing that part.
Okay.
Sir, another question. It is on the screen. What will be the maximum fault rupture area, maximum length and maximum width is available in our Earth for an earthquake, and what will be its corresponding magnitude?
Actually, I'm sorry, I couldn't hear. Where did they say where that earthquake was? Can you repeat the question?
Sir, his sir, question is on the screen, sir. Question is on the screen, sir. What will be the maximum fault rupture area, maximum length and maximum width is available in our Earth for an earthquake, and what will be its corresponding magnitude?
Okay, actually, that's a good question. So every time we get a bigger earthquake, people say, well, what's the maximum size? And I mean, there's some not very scientific, but people have once given the answer, well, if the earth splits in two, then that's a magnitude 15 or 16 or something like that. But realistically, if you just look at the zones of, subduction fault or things like that, and you take the longest length of a subduction zone, and if it happens to go all in one earthquake, you can probably get something, maybe not a 10, but a upper 9. If, say, the whole west coast of South America from Antarctica to Mexico broke in one earthquake, then you can say that might be the maximum size. The problem is you need kind of a very smooth, straight fault for the earthquake to continue. And if there's lots of irregularities, it'll probably stop the earthquake. So it's probably very unlikely that you can have such a very, very long length go in one earthquake. So probably, and I say that with a little bit of doubt, but over 100 years of active earthquakes and paleo earthquakes, probably the maximum size earthquake is around 9, or maybe upper 9, something like that. Chile was 9.5. Maybe you can get a little bit bigger, but it's probably hard to get too much bigger than that.
Yeah.
Okay, sir. Sir, Sumala sir shared another feeling that the 1950 Assam earthquake at the junction of the Himalayas and Indo-Burmese used be in that list of giant earthquake. Somehow it does not feature in there anywhere. So sir shared another feelings, and sir also conveyed his greetings to you, sir.
Okay. So actually that my figure wasn't complete. I just showed some of the very largest 9s, and then some of the, for example, some smaller ones there. But yeah, I'm sorry, and it's not a complete list of all the earthquakes.
So thank you, sir. Thank you, sir. Now there is one quiz session. The students are organizing this quiz session, and Jim sir, you will be asking the question. So over to you, Pooja, please.
Yes, ma'am. So we request you to ask one question. The answer we want would be the one-word answer. Can you ask such question to our participants so that they'll drop their answers in the comment section, and we'll be choosing the winners now. So is that okay for you?
You want me to ask a question?
Yes, sir. One question.
From your lecture.
For a participant from your lecture, sir.
Okay. Let's see.
So
okay.
You can take your time. Yeah.
Okay. If you can see in the ocean, and you felt the earthquake, and you see a tsunami coming, you see the white waves, about how much time do you think you have to get away from the shore before the large wave will endanger your life.
Yes.
So participant, you can drop your answers in the comment section. So let us wait for a few seconds and they'll be dropping their answers.
Sir, you will be choosing the correct and fastest answer, sir.
Actually, I don't. In the comments, I don't see the answer coming in.
So we are displaying it on the screen right now. So let us give them few more minutes, or if you can let know the answer, we can select the winners.
Actually, I'm sorry. In the comments, I don't see answers to that question.
It's coming
One
up in the
answer.
comment section.
I see something. Okay.
Three answers have come so far.
Okay, there's a few more.
There are so many answers coming up, sir.
Yeah, most of them are about 20 to 30 minutes. There's one that says 10 seconds. There's one that says 7 minutes,
Yeah.
20 minutes, 3 minutes. Actually, it's probably not it's hard to judge when they're just giving numbers. But sort of generally 10 to 20 minutes is probably reasonable.
Okay.
For seeing things, seeing a wave, and before it reaches the shore. 30 minutes is probably a little bit long.
Pooja, you choose
Yes,
answer 10 to 20 minutes.
Yes, ma'am. I'll be doing that.
And the fastest one, yeah.
Thank you, sir.
So, I mean, it's hard to choose.
We'll be choosing it, sir. We'll check from the comment
Okay.
section and we'll let you know the winners, sir. You can announce them.
But I think everyone that sort of gives numbers in sort of that 10 to 20 minute range probably was listening to my lecture.
Yeah, Pooja, there is one answer 10 minutes by
Yes,
Tapas
ma'am.
Rai.
Yeah, we just have to check the fastest one also, ma'am.
Yeah, that is, you check.
One
So-
is 15 minutes from Om Sudhakar. 10 to 15 by Sultan Ahmad.
Yeah, so I think that the answer is, of course it depends on lots of things like how far away you can see and where you are and all that, but roughly 10 to 20 minutes is
Yeah.
reasonable kind of
We
time.
have a person by name Sultan Ahmad who has been answered 10 to 20 minutes. And he's
Yeah.
the fast
Pooja,
type.
Pooja,
Yeah, yes,
we
ma'am.
are in organizing committee, so we will not answer. Answer will be given by only the participants.
Yes.
No, man. Sultan Ahmad is some participant, ma'am. He's a
Oh,
participant.
acha. Fine. Then fine.
Sultan Ahmad.
Okay.
Oh,
And
Good. Well done.
Okay,
so
congratulations.
and we have Ritik Pandey as well, who has answered 15 minutes.
2. You want to
Sultan
select three?
Ahmad, Ritik Pandey,
Ritik Pandey. Okay.
and Prashant C. Ramtekar. So we have 3 names: Sultan
Okay.
Ahmad and Ritik, and then we have many more actually. We just have to see the Prashant C.
No,
Ramtekar.
yes.
So
You have
these
to see
3 are
that.
winners.
Yeah.
Congratulations to them.
Okay.
Okay.
So
Thank you, sir. Thank you for the question.
Okay.
And thank you, Professor, for a pragmatic session on seismology. And it was so much informative one. And thank you, Seema ma'am, for chairing the session.
Thank you,
Hey,
Pooja.
thank you.
thank you, James.
See you later.
And we can wind up this session and
Thank
we
you.
can start our next second technical session by 11:10 a.m. Thank you.
Okay. Thank you. Thank you.
Thank you.
Welcome back, everyone. Welcome back, everyone. Looking forward to the second technical session. This session will be carried out by our co-convener of ASSHEE 2020, Dr. J.R. Kyle, sir. Dr. J.R. Kyle, sir, is a retired Deputy Director General for Geological Survey of India. He is also CSIR Emeritus Scientist, Jadavpur University, Kolkata. Presently working at the Institute of Seismological Research, Gandhinagar, India. He has also visited several universities in countries like UK, USA, Russia, New Zealand, Australia, China, Japan, France, Italy, Germany, Austria, Norway, and Mexico. He has been honored with the National Award 1994 by Government of India, also Decennial Award 2010 by the Indian Geophysical Union, and the list goes on. Today, sir will be delivering lecture on seismological data analysis and interpretation, large SCR earthquakes in India. I request Professor Ruben, sir, to chair the session. Over to you, sir.
Okay. Please start, Professor Kaya.
Yeah. Am I visible?
Yes,
The
we
Yes,
can
first
sir,
slide.
visible.
Okay. Thank you, Pooja. And thank you,
You're
Professor
welcome, sir.
Ruben Tatevosian, yes, for chairing the session. And it's my great pleasure to be with all the participants and the organizing committee and the chairman and the anchor Pooja here. So now in the morning, we had a very exciting lecture on tsunami and also, on the Tohoku earthquake. And we have learned that how shaking was taken care of by the engineering structure, but not the tsunami. So we had a very wonderful lecture in the morning. Now I will try to make some make some points clear to the particularly to the students and to the young researchers what the seismologists do with the data, with the seismological data, how we try to understand the earthquakes, how we do the data analysis, and how we try to interpret in terms of active fault or whatever and its mechanism. So I'll try to give a very brief introduction to these techniques and then switch over to large SCR earthquakes in India. So let us try to see these slides. This slide shows how the Indian subcontinent is tectonic setting, or how the Indian plate is moving from the Carlsberg Ridge. The Indian plate has moved from last 71 years and how it has come and now on head-on collision with the Eurasian plate. So today, this is the present situation of the Indian plate. Its whole Himalaya has come up due to the collision tectonics over here, and there is subduction tectonics along this Burmese arc and the Andaman Sumatra range. The oceanic part of the Indian plate is subducting, and the continental part of the Indian plate is on head-on collision, and that is the seismicity scenario of the Indian plate. You can see how all along the Himalaya the collision tectonic earthquakes are there, and in the Burmese arc, some subduction tectonic earthquakes, though it is not a ocean continent situation, but it's continent situation, but still it seems a atypical subduction is going on over here. So that is causing deeper earthquakes along the Indo-Burma arc, and which is connected with the Andaman and Sumatra and Java range. And if we see the sections, and this is the Carlsberg Ridge, where from the Indian plate is spreading and moving to the north, and on head-on collision with the Himalaya, Eurasia over here, and subduction goes on over here. Now, if we take the sections of the earthquakes from Indo-Burma to Andaman to Sumatra to Java, you find that along the below Indo-Burma, earthquakes are deeper, down to about 200 kilometer depth. In Sumatra, they are up to 450, or furthermore. And if you go further to the Java Trench, you'll find that earthquakes are more than 660 kilometers or so. So that is called Benioff zone, how the subducting plate is getting subducted along the trench and the earthquakes along the subduction zone. So they are deeper earthquakes. On the other hand, in the Himalaya, we don't get deeper earthquakes. This is on head-on collision, like this Indian plate is moving and the Eurasian plate, there is head-on collision. Indian plate basement is gently dipping, so earthquakes are shallow in the collision zone, whereas earthquakes are much deeper in the subduction zone. If you see how the Pacific plate is just now, Jim has explained how the Pacific plate is subducting and causing a lot of earthquakes along the Japan island, and this subducted plate is going down and again coming as a volcano. So this is our present scenario of the Indian plate, and we just move on the large earthquakes in Indian subcontinent. Over the last 200 years, as you all now come to know that, even their 400 years history of earthquakes in Japan, they had no clue of the tsunami earthquake like that of Tohoku earthquake. So our data is, I think, instrumental data is hardly 200 years old, and we have yet to learn. The science is so young, and instrumental data also is much young. So that way, I repeat that the earthquake data are not sufficient really to predict earthquakes yet. But as on today, we can see that about in last 200 years, we have some 30 devastating earthquakes in India, and some 1 million casualties due to these earthquakes, and also huge property loss. So these you see in the Himalayan part, there are a lot of large earthquakes. Large earthquakes means magnitude 7 and above, and there are some 4 or 5 strong. The great earthquakes, that 1950 Assam, 1897. Of course, this is no more a Himalayan earthquake. We consider it as a intraplate earthquake. The 1897 Shillong earthquake, the 1934 great Bihar Nepal earthquake, the 1905 Kangra earthquake, and most recently the 2015 Nepal earthquake over here, 7.8 or so. So all along the Himalaya, we have large and great earthquakes. And if you see in the northeast part of the continent, you can see there are so many large earthquakes and 2 great earthquakes, 1950 and 1897. And there are some 20 or more large earthquakes magnitude 7 and above. So this part of the country is most active. And if you come to the intraplate region, this part, of course, as I explained, there is some subduction tectonics going on. And then this Himalayan arc and the Indabama arc meeting here. So this is more complex zone. So we are getting a lot of earthquakes here. But in the intraplate zone, if you come, the earthquakes are not so intense, but still there are strong earthquakes, large earthquakes, particularly the western part of the Indian Shield, that is that Bhuj area or Gujarat, that has experienced some 2 or 3 large earthquakes magnitude 7 and above. And then most recently we had the Kilari earthquake in 1993, Koyna earthquake in 1963, and Jabalpur earthquake in 1997, and also Delhi earthquake. It was, of course, old earthquakes from magnitude 6.5 or so. So though the intraplate region is less frequent with strong earthquakes, but they are not seismic. They are the tectonic stress from the Himalayan collision zone is transmitted to the inner part of the plate, and we are also getting strong earthquakes in the middle of the Indian plate, like that of Kilari, very recent earthquake, and like that of Bhuj, also 2001 earthquake. So this is the large earthquake scenario in the Indian plate. And if you look at the seismic stations, I think we had first seismic station in 1899 after the 1897 Shillong earthquake. The first station was established in Calcutta, in Alipur. And since then, there was something like 30 or so instruments. And after the Kilari earthquake, with the recent broadband seismological instrumentation, after the Kilauea earthquake in 1993, since 1996, India is now equipped with some 100 broadband stations all over the country, and some cluster of stations in Northeast India, and some cluster of stations in the Himalaya region, and some special dam project or so. So this is the Indian scenario of instrumentation. So our instrumental data is right from early 20th century, means since 1900. So we are hardly about 100 years of instrumental data. So now, what we do with this data? This earthquake we are recording by seismological stations. Now, what we do? What we try to understand from these records? That will be particularly for the young students who have joined to this workshop. Now, our first job as a seismologist is to locate the earthquakes. Now, if you see here, this is the analog record in those days before 1980s in India. And then since 2000 or since late 90s, we have started digital record. So this is digital record, digital seismogram, and this is analog seismogram. So these are all very micro earthquake instruments, and we can record very small earthquakes also if we go to the site and record the aftershock. So these are the very valuable data that we record after any large earthquake. And the national network, which I have just now shown you, which is operated by the then India Meteorological Department, now National Seismological Center. Those 100 broadband stations are recording around the clock the earthquakes all over the country. But with the portable instruments, we can go to the site, we can try to record huge number of earthquakes, micro earthquakes, and we can try to understand the tectonics and active fault and so on. Now, after recording the earthquakes, how we locate? Before the computational techniques came, say before 1960 or so, till 1960, IMD was locating earthquakes by manually. If you know the earthquake, suppose this is the earthquake is occurring here, and this is the epicenter, and we call it hypocenter, and this is our station. So this is called epicentral distance, and this is called hypocentral distance. D is the hypocentral distance, and X is the epicentral distance. And if you can record the first P arrival and S arrival, then this difference of P arrival and S arrival, there are two body waves that we record by the instrument, and then the surface waves we record. That you have all read about seismic waves in your class 12 or course. So those P wave and S wave are recorded, and then if there is surface wave also, that we can also record. That is only for the teleseismic events we get surface wave mostly. But for the local earthquakes, we are interested in the P wave and the S wave. And if you know the difference between P and S wave, then you can estimate this, this Ts minus Tp, it will be about something like, the D into 1 by Tp minus 1 by Ts. So that way you will get something like 8 times of S minus P time. That time interval between P and S, that time interval into 8 is your approximately that distance. So suppose this time interval is 10 seconds, then this D is about 80 kilometers. So you know approximately the distance of the earthquake from your station, from your record. So if you have got some 4 or 5 stations around the earthquake, then you can draw a circle with that approximate S minus P time, respective S minus P time, and you can draw the arcs, and those arcs will intersect at some place, and that is the area of your epicenter. So that is how the epicenter is to be located manually, say before 1960s or so. And then if you know the epicenter, you know the epicenter distance X, then you can also estimate the D from this formula and also H. So this is how the earthquake location and earthquake epicenter and depth was to be given in the earlier catalog. But since 1964, things have improved with the global seismic network, and the computational method has come. So we can now locate earthquakes with a much better precision by least square method. It's a software that Hypo 71 or session software we use. It's a least square method. Just you have the arrival time of different stations. You assume some velocity model of that area. You also give some approximate depth of the earthquake. Then the regression analysis will start, and it will estimate the computed time and see the difference between computed time and the observed time. So that is called residual. And as long as it gets the minimum residual or minimum RMS value, the regression will go, and it will give you the best possible location of the earthquake, and that will be your epicenter, and also depth is estimated, and also the origin time. So that is how the computational method, the least square method, works. So that is the routine method nowadays in every observatory to locate earthquakes computationally, taking the P arrival time and S arrival time, and also assuming a local velocity model, or for the global earthquakes, global velocity model. Now, much better precision can be obtained by some advanced technique like joint hypocenter method. These topics are all PhD topic. So you can also, but because your stations are not all uniform geologic formation, so there will be station correction. So that station correction can be estimated, evaluated from this method, and you can incorporate the station correction, and you can come out with a better location. Then further precision can be made by double difference hypocenter method. That is, you can take the very close to earthquakes, you can take the difference of their time arrival between E and S, and you can also do the regression to find out the best possible residual. So that way you can also much precisely locate by double difference method. Then further precision you can have with simultaneous inversion. That means for these two methods you have assumed velocity model, but in this simultaneous inversion method you start with the assumed velocity model, but you also evolve the epicenter, the depth, the origin time, and also the velocity model. So it simultaneously does the inversion to get to the earthquake parameters and to get to the velocity structure of that area. Suppose here I have shown an example how the Pacific plate, high velocity subducting lithosphere, Pacific plate is subducting below Japan Trench, and this is the overriding Japan continental plate, and the volcanic area are showing lower velocity. The red shows the lower velocity below the volcanic area, and this is the blue shows the high velocity subducted plate. So this is how you can also image this structure below your network, and you can also do much precise location of the earthquake. So this is what is our preliminary job up from the earthquake records. We do routine locations. We do further refine the locations with different computational methods. Then next job is to estimate the magnitude. You all heard about the Richter magnitude, and this is the first scale to estimate the earthquake size. What is the size of the earthquake? Means how much energy it has. The magnitude and intensity are two different scales and two different objects. The earthquake magnitude gives you the estimate of the energy of the earthquake, that as you have already heard from Professor Gupta, that 1/8 magnitude earthquake is about 1,000 atom bombs energy, and 9 is about 30 or 32 times of that. So the magnitude is the estimate of energy, and that first scale was developed by Richter, and he assumed that wood Anderson seismogram, if in that instrument, if you have a record of earthquake, then that S-P time, as I said, it gives you the distance, approximate distance, or you have got the S-P time scale over here. He developed this nomogram based on some assumptions. He made an assumption to develop this scale. He made an assumption that an earthquake at a distance of 100 kilometers If it is recorded with 1 millimeter amplitude, then that earthquake is of magnitude 3. So with that assumption, he developed this nomogram, and this nomogram works. This scale works till today, much compatible with the modern theoretical scales. I will come to that. So suppose you have a S minus P time and maximum amplitude. So S minus P time over here and maximum amplitude you measure, and then that is the scale over here. So say it is here 23 millimeter and 24 second is the S minus P time. You join these 2 points and this is the magnitude scale. So you get the Richter magnitude. But this scale, as I said, is very popular scale, and till to date it is used. But this scale gets saturated over a magnitude, say 6.5 or 7. Beyond that, I think the most theoretically based magnitude scale now has come, that MW, which is just now explained by Jim, that we can estimate the MW from the seismic moment. So MW is most, say, modern scale and a stable scale, even before, beyond the magnitude 7, 8, 9, it does not get saturated. So MW is nowadays most, again, used scale for the higher magnitude earthquakes, but Richter scale is still popular. Then we have different magnitude scale like body wave, like surface wave. This is moment magnitude, and then duration magnitude, duration from the duration of the signals, and then from the damage, from the macroseismic, from the damage pattern also, you can estimate some magnitude. So there are many scales, and you must know what's because you will be seeing in the catalog that some seismologists is saying that magnitude 7.2 in Richter scale. Some are saying it is 7.3 in MW scale. So we have to know that what scale we are talking about. So it is not that because the magnitude you estimate from any scale, it is normally consistent at each station. So the magnitude is fixed for an earthquake, but intensity is the degree of damage. It varies from place to place. In your epicenter area is the maximum damage, so it will have a higher intensity or higher damage. And as you go away from the epicenter area, your shaking or your damage is much less. So accordingly, the scale is designed as a descriptive scale. So there are 3 different scales. First scale was Rochefoucauld scale, then modified Mercalli scale. It was 1956, it was modified. Then in 1992, the MSK scale has come, which is now is mostly used in modern isosceles map. But in the earlier maps, you'll find mostly modified Mercalli scale. It was also popular like Richter scale of magnitude scale, and modified Mercalli scale in intensity scale. It was very, very popular. But now we are using MSK scale. And similarly, we are also using MW scale for the earthquake magnitude. So I think this much is enough for today's lecture. Now, I will go how we do the source mechanism study. The source mechanism is how the earthquake has occurred, or what type of faulting it generated the earthquake. So to understand that, the elastic rebound theory was developed after seeing that 1904, that California earthquake, the San Andreas fault, along the San Andreas fault, it was visible how the formation displaced. So based on that, observation, Reed gave a elastic rebound theory, and in this theory he has said that the rock takes up the stress, and at certain point the rock breaks and rebounds like a spring. You go on winding the spring, and at certain point the spring rebounds. So similarly, rock breaks and rebounds. So that is the observation, real observation in along the San Andreas fault, and based on that, the ground motion also was hypothesized that if this is the fault, and if this type of movement is there, and if you consider a orthogonal plane, then in this quadrant your instrument will record down motion of the P wave, and this quadrant your record P motion will be upward. So when the P wave first comes, you always experience a boom sound that either building has gone up or down. So that is the first ground motion that is recorded by seismogram. So that ground motion can be, or fast motion can be used to find out these two orthogonal planes, because this is a known fault plane here, and you have assumed the orthogonal plane. But if this is the, if this is the fault plane, if A dot is the fault plane and this is the auxiliary plane, then your this fast motion are also explained by this A dot fault movement like this. So it is called double couple hypothesis, means by two orthogonal plane, we can separate out the fast motion of the earthquakes, and then either of the orthogonal plane is the fault plane. So based on this, we started to try to plot this fast motion of the P wave, how the P wave is coming to your station. So suppose your P wave coming up, and you know the angle of incidence from your computation, and the azimuth of the station based on your with respect to your epicenter, that is also computed. So you can plot this. You can plot this point whether it has come up or down. So that can be plotted by a geological technique. They call it upper hemisphere plot. So that plotting technique we use to we plot the up motions and down motions, and then we separate out by two orthogonal plane to come out with the inference of a fault plane solution. So these solutions could be like this type of solutions, like, before that, let us try to understand the dynamics of faulting. When the tectonic stress, we have got three major principal stresses: the compressional stress, the tensional stress, and the intermediate stress. So when your compressional stress is horizontal dominant, then you get a thrust faulting. Means your block is under stress, compressional stress. So one block goes above the other, and that causes thrust faulting. And that is a symbolic, beach ball presentation. And when the rock is under tensional stress and there is a fracture and one block goes down, then that tensional stress is dominant or horizontal, and you come out with this type of fault plane solution. And when your, both the compressional stress and tensional stress are horizontal, then it's a cause of shear faulting, like this type of shear faulting, and you get a strike slip faulting, and this is the symbolic representation of strike slip faulting. So here, after this plotting, you can come out with this type of solution or this type of solution or this. So there are various types of solution, and suppose this one is a almost pure strike slip, and this one is almost pure normal faulting. This is the normal faulting where tensional stress is horizontal, and here compressional stress is horizontal. Or a pure thrust faulting, a compressional stress is horizontal. So pure thrust faulting or pure normal faulting or thrust faulting with some strike slip component or pure strike slip faulting with some, so these are the different types of mechanism that we come out with our seismological fast motion data. And also nowadays, this is the basic of fault plane solutions, how we come out. Now with the advent of the digital seismograms, we try to do the inversion, the waveform inversion, and we also come out with the fault plane solution. This part, this particular observation we made for the IIT ISM broadband data, and we found that a strike slip faulting occurred for this particular earthquake. So this fault plane solution by waveform inversion, we have kept a separate lecture by Dr. Shantanu Barua tomorrow. And so this is the fault plane solution that we can do to understand the earthquake mechanism. Now, if we have a look into this tectonic map of peninsular India, you'll find that the Himalayan collision zone, then the Indo-Gangetic plain, and then the peninsular sill, means stable rock continental region. So here, as you have seen, Himalayan is having the lot of earthquakes due to collision tectonics, but within the interplate region, we have a few recent earthquakes like 1963 Koina by strike slip mechanism. Now you understand this beach ball, this is strike slip faulting, or the Kilari earthquake by thrust faulting or reverse faulting, or the Bhuj earthquake also by reverse faulting or thrust. Reverse faulting means when the thrust plane is more than 45 degree, we call it reverse faulting. So today, I will show you what we have done with the seismological data to understand 3 or 4 intraplate earthquake, SCR earthquakes, means stable continental region earthquakes. So those are Kilari and Jabalpur and Bhuj. And I will take also that 1897 Shillong earthquake, which is also considered to be a intraplate earthquakes. So these 4 earthquakes we will try to understand based on our recent observations, recent records. Now, if we look into this earthquake, this earthquake occurs somewhere here in the middle of the stable continental region. There was no earthquake record from this part of the country, and this was supposed to be a very stable part of the country. But one fine morning, we found that some 20,000 people were killed by an earthquake of magnitude 6.3 or so. It was a shallow earthquake, typical intraplate earthquake, very shallow earthquake, and it caused devastation like this. And there was only few hundred meters of rupture on the surface, and no long rupture was found. But since it was a shallow earthquake, at least some ruptures were observed, and the engineering structure also failed, and the villages were total collapsed. So immediately after the earthquake, we, from the GSI, we took the portable instruments, micro earthquake instruments, and surrounded the area with a local network. These triangles are the stress seismic stations we put, and this is the maximum damage area where all the aftershocks are recorded, and also the main shock in the middle of the maximum intensity, and that was of the order of 8 intensity, Romanian 8, and that means quite a big damage happened here. And if the total damage occurs, we give the intensity of the order of 10. So this was of the order of 8 intensity, and magnitude was MW 6.3. And our aftershock data, the main shock was recorded by the global network as well as by the national network, and they come out with a epicenter over here and a focal mechanism like this. Now you can understand this is a more strictly it's a reverse faulting or thrust faulting. And the aftershocks are recorded by our temporary network. And since the earthquake was shallow, we made a very close network, and we recorded something like 200 aftershocks, magnitude 1.5 and above. And those earthquakes we studied, and all the aftershocks are within this maximum intensity zone. And when we took and we also did the focal mechanism solution. The main shock solution was done by the global network, also by the national network, IMD network. But the aftershocks we recorded and come out with 2 types of solutions. One is reverse faulting, one is strike slip faulting, or normal faulting dominated with some strike slip component. Now, when we observed the cross section of the aftershocks, north-south cross section, there was no fault, geological fault mapped in this area, because the whole area is a Deccan cover. It's a Deccan basalt cover. So there was no surface fault on the surface to know which fault is activated. And there was no record of earthquakes for thousands of years. So there was only a Tirna river is going like this, east to west end of Tirna river, and one river, Tirna tributary, is north to south extending. Only these 2 rivers are there, and though no geological surface fault is there, mapped there. So we had no clue which fault is activated. Now, to understand that, the active fault, we took a section of the earthquakes, aftershock sections, and this is north-south section, this is south, and this is north. And we found that the aftershocks are like this, and the main shock, the star mark, at a depth of 6 kilometers, and the aftershocks are also at a depth of within 6 to 12 kilometers, deeper aftershocks. And the shallower aftershocks are like this, these cross symbols. And we could make and this is the surface rupture. We could see that a dipping plane is like this, and on which the main shock and the deeper aftershocks are lying, and the shallower aftershocks on both sides of the of this line say this is our tentative understanding of the this could be the fault plane. So a south dipping fault plane might have caused these earthquakes. That is our understanding, and that we infer from this fault plane solution. In this, there are two types of two planes are there, and this plane, which is south dipping, is the matching with this our aftershock sections, and this is about 70-degree angle, and this angle is also for this fault plane solution. This nodal plane, we can find out the angle of that deep of that plane, so that also matching. Then we try to understand what is the interpretation of these deeper aftershocks, thrust faulting or reverse faulting, and the shallower aftershocks, these clustered by tie-slip faulting. So we came out with a model like this, that the upper block, as a whole, it is thrusted up and to generate the main shock, and the upper block itself, which is at a depth of say 0 to 5 kilometers or so, those aftershocks are caused by this, by this tie-slip movement of the upper block. So it's very complex type of model that two intersection of the two faults. One fault is east-west, that is causing, and south dipping, that is east-west. This is the east-west trend of the south dipping fault. So that is causing the main shock, and the aftershocks having a fault plane like northwest southeast and having some tie-slip component. So this fault plane of the shallower aftershocks, which is matching with the Tidna tributary, and this this fault plane, Tidna river, rather let us say this is our interpreted fault plane, east-west fault plane, south dipping, that has caused the main shock, and this tributary, which is northwest southeast trending, that has caused the shallower aftershocks, and deeper aftershocks and the main shock caused by this south dipping fault. And so this is the model we try to understand, and then we try to do the seismic tomography using the P and S level data. As I said, these earthquakes were located by some special technique, but then we use this data for seismic tomography, and at different depth level you can take the seismic tomograms, and at a depth of 3 kilometers, let us say at a depth of 6 kilometers, you can see that there is a east-west trend of low velocity. This faded area shows the low velocity zone, and this area shows a high velocity zone. There are other high velocity, the heterogeneous structure is there, but you can see that main shock occur over here at the high velocity zone, and the east-west low velocity structure is also there. So at the end of that fault, this main shock occur, but in this tomogram at a depth of 3 kilometers, that slice of the crustal heterogeneity that you are getting from the tomography structure, you find that there is a low velocity structure. Low velocity means this fault zone and rocks are crushed, so it is giving low velocity. So the northwest southeast, this low velocity structure is matching with our fault plane and also with the Tidna tributary. So our interpretation was that the east-west trending Tidna river, which is the surface expression of a hidden fault, which is south dipping, that caused the main shock and the deeper aftershocks. And the northwest southeast trending Tidna tributary, that's a shallow fault up to 5 kilometer depth, and that caused the shallower aftershock with some tie-slip movement. In fact, I share my experience that when we sent this paper to BSSA, without revision, the reviewer gave a very good comment that it is a textbook type of observation. So this was our first, with a digital instrument, first micro earthquake aftershock investigation results of the Kilari earthquake. Then the Intrapay region, another earthquake occurred, that is 1997 Jabalpur earthquake. This earthquake is bit, again, every earthquake is surprise and every earthquake is a lesson. That's what Jim also explained. What a surprise that earthquake, Tohoku earthquake. Similarly, you see here, this is in the Narmada Rift Zone. The Narmada Rift Zone is separating the northern seal and the southern seal, and there's a long rift zone from from west to east, about 1,000 kilometer long rift zone, about 50 kilometer wide. And in this rift zone, there are so many large earthquakes are strong, not large, all strong earthquakes match to 6.5 or 6 point so. So this is a rift zone means when the Indian plate was moving because of the internal tension, it was broken and a rift is formed. So in that rift zone, the Jabalpur earthquake is this one, which is shown by this black circle, and this is the mechanism of the Jabalpur earthquake. So this Jabalpur earthquake occur. There are two faults. One is Narmada North Fault. One is Narmada South Fault. But in the DSS sounding, which was carried out by NGRI, they found the Narmada North Fault, and they also found the Narmada South Fault. But there is another parallel to this Narmada South Fault. There is another fault which is here, FF dot. That was investigated by the Geological Survey of India geologist. They found that along the Narmada South Fault there is another fault, which is in that fault zone, also named as Narmada South Fault. So this is the fault zone, and this is the main shock epicenter, and these are our triangles, are our seismic stations, and all the aftershocks occur in the footwall area of the of the fault. So this is the main shock, these are the aftershocks, and the maximum intensity on the other side of the fault. So again, a bit different results from that of Kilari earthquake, where Kilari earthquake and the aftershocks are within the maximum intensity zone. This intensity is also 8, but this is on the other side of the fault, and the maximum damage in this side, at this side of the fault, on the footwall side of the fault, and on the hanging wall side of the fault, the main earthquakes and the aftershocks occur. And when he took the section shows that the main shock, and this is the first large earthquake that was recorded by our national broadband network, and the depth was very well estimated by IMD, the then Dr. S.N. Bhattacharya. That paper came. So the depth was 35 kilometers for this Jabalpur earthquake, and our aftershocks are also from 35 to 42 kilometers, and means the rupture propagated downwards possibly, and all aftershocks are at this depth range at the crust mantle boundary, and the crust mantle depth is about 38-40 kilometers. So at the crust mantle boundary, the main shock occur and the aftershocks occur, and there were not many aftershocks because the depth was there, and it was also on the other side of the fault the maximum damage was observed. So these are and again from the national network and from the USGS, they both observed that it is a reverse faulting with some strike slip component, and this is our aftershocks mechanism. We also find the reverse faulting with some strike slip component. So this south dipping nodal plane, or in a main shock, this south dipping high angle, maybe 50 or 60 degree angle, and almost east to west. This trend, of course, also like this. So this nodal plane is this fault plane, and this also matching with the aftershocks. So aftershocks and the main shocks all occur at a deeper depth with a south dipping fault, that is that fault FF dot. That is the southern boundary of the Narmada South Fault. So that was our observation for the Jabalpur earthquake. So we tried to understand the aftershocks mechanism, main shock mechanism, and tried to interpret the in terms of the tectonics for this region. Means the rift which was formed due to a tensional regime when the plate was plate movement was there something like 50 million years ago. The rift was formed by tensional regime, but now the rift is producing earthquakes by thrust faulting or reverse faulting mechanism. That means it is now the inversion tectonics, we call it. That means the no more tensional regime is prevalent. Now it is under compressional stress due to collision, head-on collision at the north, and the compressional stress is now generating earthquakes by thrust faulting mechanism. So we call it inversion tectonics. Now this is another significant, earthquake which occurred, as I said, Kutch Rift and Narmada Rift, the Cambe Rift. All these rift basins are here, big, main 3 rift basins, and the main shock occurred here in this triangle type of zone, your aftershock zone, and this is the mechanism. Again, a reverse faulting with some style component. And these are the past earthquakes in the Mount Abu earthquake and in the Satpura earthquake, and this another earthquake was there in Anjar in Bhuj area. So we can see that mostly they are by reverse faulting and with some style component. Now this figure is showing at what time the first P wave arrived. This is a inspection bungalow where we went to have some accommodation. We immediately within 24 hours we moved to this area to record the aftershocks, because the main shock is recorded by the global network as well as by the national network. But from GSI, we always used to move to record the aftershocks, and they are huge in number, because once the large earthquake occurred, it followed by huge number of aftershocks. So when we came to this IB, we found that the exact time of the arrival time in that area, it was 9:55 in the morning. So that was that worked as a seismoscope, without any time series, but it has recorded the time of the arrival of the P wave. Now again, this earthquake caused huge damage. As you can see, a good building has totally collapsed, and it was given something like maximum intensity, something like 10 by our geologist team from the GSI, and that village was total damage. There was crustal, there was no surface rupture. That was a spectacular event, such a 7.7 magnitude event, MW 7.7. But it did not give any rupture, but rather there is a crustal deformation, of course, was there, and liquefaction was also there. So there was liquefaction and total damage, and this was the isolational map by Pandey and others. And now this is our seismology team. We tried to monitor the aftershocks, and as I said, this is the main shock, and we had some 13 to 14, digital and analog instruments over here. And these are the aftershocks that we recorded. And then again, by some technique, some homogeneous method technique, we tried to precise the aftershocks locations, and try to understand their focal mechanisms. So this part of there are 2 wings, right hand wing and left hand wing, and this wing aftershocks are showing some left lateral style slip mechanism, and this aftershocks are showing defined mechanism, right lateral style slip mechanism, and this is the mechanism of the main shock. So mechanism of the main shock and the aftershocks are studied in terms of to understand the thermotectonics of that earthquake. So when we took a section, now these aftershocks are now relocated by seismic tomography, and then these sections are taken. This is east-west section like this, and north-south section. And in the north-south section, you can see east-west section. You can see two arms of the aftershock, and in the north-south section, you can see a near vertical structure, and somewhere here is the main shock, and a near vertical structure is there. And when with depth and time we plot the earthquakes, you find some bimodal seismicity. Earthquakes are much intense at a depth of 15 to 25, then from say 20 and 25 to 35, like that. So there are bimodal seismicity observed, and a vertical structure is observed. Now, based on this mechanism of the earthquakes, we tried to make a model. This section is this section we have brought over here to do the modeling, and we try to model that a near vertical or south dipping zone has caused this earthquake, and a lot of aftershocks are from 15 kilometer depth to 35 or 37 kilometer depth. So this is the seismogenic part of the crust, which has generated main shock and the aftershocks. And upper part, no much aftershocks from say 0 to 15 kilometer, no many aftershocks and no surface after either. So we try to say that two faults might be, and this fault, which is locally known as Bachao fault, and other two faults, some lineament, could be the intersection zone has caused this earthquake, and these are the left lateral movement and right lateral movement. So that was our earlier interpretation. And then we also studied the B-value mapping. B-value, you all understand the number of earthquakes and the magnitude are plotted, and that shows a linear relation. Means with one magnitude down, number of earthquakes goes 10 times if the normal value of B-value is 1. So that B-value for each grid, some 10 kilometer by 10 kilometer grid of the area are estimated, and their map is made, color map is made, and that shows two arms of the aftershock zone are having two different type of velocity, the B value. So that also is observed from the B value and from the from the mechanism also. And this is showing our tomography results. This is P value, VS structure, and VP by VS structure. In this interpretation, we try to say that two low velocity zone and in between the high velocity zone, and that was the region for the depth of 25 kilometer, and that was the region for the main shock, and also compatible with the S velocity, and there was some liquid in the VP by VS was low, so that shows that there was some liquid there, and that actually the velocity, that presence of liquid maybe is causing huge aftershocks. This is our only past 3 months record, and that has given something like 3,000 aftershocks, and we have located some 300 earthquakes. And then we did further work recently. Now there is another interpretation by another group of seismologists. So every earthquake is, as I say, is a lesson. So this Mundol and others from NGRI, they also published a paper in the BSSA, and they found the similar type of aftershocks, two arms of the aftershocks and main shock in the middle. And they try to say, and this is the Kutch mainland fault over here. In the rift zone, there are two boundary fault, and in the middle of the rift, there is a Kutch rift zone, Kutch rift mainland fault. And there is a South Wagat fault, and these are the geologically mapped fault. But they said that this boundary is the North Wagat fault, and that boundary is giving is a fault zone. And they try to examine the section and try to extrapolate with that boundary. They named it North Wagat fault. So they call it a North Wagat fault, which is not geologically mapped by the geologist. Here Pandey's publications, here SKB's publications, they are the two renowned geologists who has worked in that area. In their model, there is no North Wagat fault. In that model, they have got Kutch mainland fault. This is the Kutch mainland fault, and this is the South Wagat fault. That is geologically mapped, and this is the model by Biswas that South Wagat fault is almost near vertical, and that junction of the Kutch mainland fault and South Wagat fault is caused the main shock. And in this model, Pandey also did not show any North Wagat fault, but this North Wagat fault was based on this boundary of the aftershocks. They gave a North Wagat fault, marked this as a North Wagat fault. But then we try to do the tomography and try to see the fault plane solutions of huge aftershocks, which is still continuing, and possibly due to the presence of the fluid. As in one lecture, Walter Mooney of USGS says that if there is a liquid at the source zone, that that causes long-term aftershock sequence. Anyway, the aftershocks which are recorded by the ISR network in Gujarat, those aftershocks of 10 years or so, we have studied. So this is 1819 large earthquake, and this is that 2001 Bhuj earthquake, and this is the aftershock area. And this aftershock area, something like 6,000 earthquakes we have recorded, and we did the tomography, and we found that that the South Wagat fault could be the positive fault for the main shock. That that seismic tomogram shows that the low velocity zone, the South Wagat fault, is extending downwards, and then at this lower crustal region, there is a high velocity structure which is accumulating stress, and that caused the fault to trigger and generate this main shock and also the aftershocks. Now, when we this relocated huge aftershock data, when we took the north-south section, again we find a near vertical structure, and then there is the fault structure geometry something like this, and this is the main shock, and these are the aftershocks. You can see no aftershocks in the upper part, and from the lower crust to down to mantle depth, there is aftershocks. So this matches with the geological model of Biswas, and this is the Giddy fault. Another fault is this is the mat fault. Another fault is activated further north of this after main shock zone. So this is quite clear that could be the South Wagat fault, and then these fault plane solutions, fault planes are plotted. Again, these fault plane solutions are taken from Mondal, and those fault planes, infer fault planes, are plotted in the deep direction, and they are found to be matching with this our infer South Wagat fault, which is the near vertical at the surface, and then it is coming like this. So possibly South Wagat fault is the causative fault, and the aftershocks are still continuing, and they are mostly, again, this rift zone, and all earthquakes are occurring by reverse faulting or with some strike slip component. And again, the inversion tectonics is the interpretation that this rift zone was produced by the internal tension due to plate movement. Now this rift zone is under compressional stress zone and causing the inversion tectonics or the thrust fault mechanism earthquakes. Now I think I have another 2-3 minutes I will take to complete my lecture. Now, another shield earthquakes, very interesting zone. I think I should touch upon this, though it was initially thought that it's a Himalayan earthquake and one of the great earthquake in the Himalayan zone, but now it is reinterpreted to be a shield earthquake, intraplate earthquake. It's much away from the Himalayan collision zone. Normally 100 kilometers away, we call it intraplate zone. So it is about 200 kilometers away, and from here also 300 kilometers away from the Indo-Burma subduction zone. So it is much away from the collision zone or from the subduction zone, so-called subduction zone. And this earthquake occurred here. And recently, a model is given. Before that, I want to tell you one thing, that this was the isoseismal map given by Oldham in 1899. That was the first largest earthquake, surveyed by the then Director General of GSI, Oldham, and that memoir is very famous. So he has given all details, and in one, and this intensity was given something like 10 to 11 for the maximum damage area over here. This is in mm scale. Richter has again modified in his book. So, and that was the wide area was felt, intensity 6 or intensity 5, widely felt area. And this is the maximum intensity zone over here. And in the maximum intensity zone, Oldham observed that boulders were thrown from their place, they are thrown out. So he speculated that this earthquake acceleration must be more than 1 G, then only this thing can happen. So that 1 G acceleration of ground acceleration is highly appreciated nowadays. That yes, that earthquake generated an acceleration of the order of 1 G. And today also, Jim has explained more than 1 G acceleration for that Tuhuku earthquake. And now, in this tectonic setting, you can see that the Bengal Basin or Bangladesh, is demarcated by thick sediment and by east-west Dauki fault, gigantic Dauki fault. And this is another fault which is called Dapsi thrust, parallel to the or offshoot of the Dauki fault. And this is the one transverse fault, Kofili fault, that also generated 2 large earthquakes over here. One is Kachar and one is 1943 earthquake over here. And this is a transverse tectonics here. And this recently, Bilham and England interpreted that This 1897 earthquake occurred by pop-up tectonics of the Shillong Plateau. And he identified from his GPS data that the Shillong Plateau is popping up. That popping up of the Shillong Plateau is, of course, reported earlier also by NGRI scientists like Purnachandra Roy and others, that Shillong Plateau is rising, and that is because of it is bounded by the boundary faults like Kopili fault and Dauki fault, and here is Dhubri faults, and here is Brahmaputra fault, like that. But Bilham and England, they proposed that there is a boundary fault between, at the northern end of the Shillong Plateau, and they named it Oldham Fault. And they say that Shillong Plateau is popping up between Dauki Fault and Oldham Fault, and that popping up tectonics has caused this earthquake. So they gave a model like this, that this is the Dauki Fault and this is the Oldham Fault. Oldham Fault is south dipping and Dauki Fault is north dipping, and Shillong Plateau is popping up, and that generated at the Oldham Fault, the south dipping Oldham Fault caused this earthquake, and they came out with the mechanism. Now, this mechanism is now based on the record outside of the country, because that time we had no instruments. So they have come out with a mechanism and also with a model. And though pop-up tectonic model was postulated before that, but with a quantified model, Bilham and England has given this model for this earthquake, that is pop-up tectonics of this. So we have seen inversion tectonics, we have seen typical shield earthquakes in Kilari, inversion tectonics in Jabalpur Rift, inversion tectonics in the Kutch Rift. Now we are seeing another greatest, I think, largest shield earthquake, interpret earthquake, Shillong Plateau earthquake by pop-up tectonics. And as you can see, this is the Indian plate is below the Burma range. It's bending somewhere here, and it is about 300 kilometers away. So this is the intraplate earthquake of the 1897 Shillong earthquake. Now, with the recent data, broadband network data run by Jorhat and NGRI that time, and we had a DST RFBR project. In that project, we analyzed something like 300 to 400, well-recorded 3 and above magnitude earthquakes in Shillong Plateau and Kopili Fault. I will not touch upon this. This is transverse tectonics, but let us try to understand what is happening in Kopili Fault zone. In the Shillong Plateau zone. Now here, all the earthquakes are showing mostly, thrust faulting or reverse faulting, you can say, strictly speaking, and in the Kopili Fault, they are mostly strike slip faulting. So the two tectonic, zones are there. One is pop-up tectonics, Shillong Plateau, generating a lot of earthquakes. One is transverse tectonics along the Kopili Fault and by strike slip faulting, and lot of intense earthquakes along the Kopili Fault. And then there is a subduction tectonics along Indo-Burma ranges, a lot of earthquakes. Then there is a collision tectonics in the Himalaya, a lot of earthquakes over here. So we are just trying to understand this 1897 Shillong earthquake and in the context of present scenario of the present record of the broadband network. Now, this is our fault plane solutions, which is showing also reverse faulting mechanism because of the pop-up tectonics, means the block is going up, thrusted up. Now, when we try to see the sections of the earthquakes that we recorded by broadband network, those sections are showing in view of this model. We can see that this is our Dauki fault. We have plotted those features on the north-south sections. Along this, we have taken a section. So Dauki fault, then Dapsi thrust is somewhere here. As I said, this is Dapsi thrust, and below this is boundary of the Bangladesh. And as you can see in Cherrapunji, you can vividly see the fault over here. The Bangladesh has gone down. So this is Dauki fault that we have plotted here. And then Oldham fault, the Oldham fault shown by Bilham and England. But geologists do not believe, GSI geologists do not believe the Oldham fault. They believe that the Brahmaputra fault is the surface feature, surface geomorphological evidence of the east-west fault, the Brahmaputra fault. This part of the Brahmaputra river, they call it Brahmaputra fault. So we have also shown that Brahmaputra fault over here. So this is the section. We can see that earthquakes are all within this Shillong Plateau, and these are the fault features. Now, when we plotted the fault plane solutions and the fault planes, we can see that the Dapsi thrust, which is is almost a part of Dauki fault, of course, and this part of the fault, this Dapsi thrust, is active, and it is showing the fault planes are matching with the Dapsi thrust, deep, and also this part, Oldham fault and Brahmaputra fault, they are not much away, hardly 10-15 kilometers away. This so-called Brahmaputra fault and the Brahmaputra river. Oldham fault and Brahmaputra river fault, and we cannot distinguish between the Brahmaputra fault and the Oldham fault, but we can see that the earthquakes are also matching with this Brahmaputra fault, and possibly the Brahmaputra fault, in our interpretation, possibly the Brahmaputra fault, we have called that Oldham fault / Brahmaputra fault. Possibly this is the northern boundary of the Shillong Plateau, and Dapsi thrust or Dauki fault is the southern boundary of the Shillong Plateau. And presently, Dapsi thrust is active, and Brahmaputra fault could be the northern boundary of the pop-up tectonics. So that is what is our understanding about the Shillong Plateau earthquakes by pop-up tectonics between two boundary faults and by reverse faulting fault. I think I have done my job, and now my conclusions are as follows. The 1993 Kilari earthquake, intensity 8, depth 7, is a typical ASSHEE, means which is shallow and in the middle of the plate, and occurred by reverse faulting. Besides aftershock location, seismic cross section, fault plane solution, and seismic tomography, we have taken the local earthquake tomography. Tomography provide fault interaction model or seismotectonic model. Fault interaction means two faults are intersecting, and that intersecting zone has caused this earthquake. And the 1997 Jabalpur earthquake, magnitude 6.6, intensity 8, depth 35 kilometer, occurred at the Narmada South Fault at the crust mantle boundary of the Narmada Rift Basin. Seismic cross section, fault plane solutions reveal seismogenic fault, and it has caused by the inversion tectonics. The 2001 Bhuj earthquake, magnitude 7.7, quite a large earthquake, I think largest earthquake in that area. And intensity, of course, there was another earthquake, 7.8 in 1819. And the intensity 10 means total damage, and depth 25 kilometer. You can see the Rift Basin earthquake are deeper, the 35 kilometer, and Bhuj earthquake is about 25 kilometer. Whereas the typical sill earthquake is only 6 to 7 kilometers. They are normally within 10 kilometer sill earthquakes, but the Rift Basin earthquakes are deeper. And this is 35 kilometers in Narmada Basin. And precise aftershock location, seismic cross section, and fault plane solutions and seismic tomography could not be done for this earthquake, but it revealed the fault geometry and seismogenic fault. The 1897, the Bhuj earthquake, yes, Bhuj earthquake we did the tomography, but for the Jabalpur earthquake we could not do the tomography because the aftershocks are much less, about 40 earthquakes aftershock. So data was not sufficient to do the tomography. You need thousands and thousands of P wave data and S wave data. And the 1897 great earthquake, it was estimated MS 8.7, but then the revised magnitude is 8.1. That is given by Biram in England and also by Arabases and Douglas. The revised magnitude, that is MW, as I said, MW is now accepted as a most modern or most theoretically based magnitude, and that is most stable magnitude scale for the higher magnitudes. So the moment magnitude is 8.9, 8.1, and by the way, the 1950 Assam earthquake was also given MS 8.7, but now the MW, revised MW is 8.4 for the 1950 Assam earthquake. And the Shillong earthquake is also at a deeper depth, and it is by pop-up tectonics, as I already told you, and our tomography and fault plane solutions are also supporting this pop-up tectonics. So I think this is what I wanted to convey about the the seismological data analysis interpretation in terms of with the recent earthquakes. Thank you so much.
Thank you, Professor Kayal, for your very interesting lecture. You guided us from very basic issues to the principal problems of the stable continental region earthquakes. So please, we are slightly behind the schedule. So just some short questions, please. So, Professor, can you see the question on your
No, not.
screen?
No, I.
Or I will. Okay, then I will read it. Very enriching session. Thanks to the creative brains behind such a great event presented to us. Is there any possibility of devastating earthquake in India in remaining days of 2020? Asked by Tapash Roy.
Is there any, what is the specific question? Is there any possibility of?
Possibility of devastating earthquake in India in remaining days of 2020.
In the remaining part of the peninsula shield area, I think this is some sort of question of earthquake prediction. And I think in the morning session, Jim has clarified that, even they have 400 years data and they never speculate the Tohoku earthquake. And we have instrumental data hardly for 100 years. So I don't think with this data set, we are yet to, able to make a model for earthquake prediction. We can only identify the earthquake, prone area, earthquake risk area, but we cannot predict earthquakes because you see the Kilari earthquake, this area was marked as a stable land, and in seismogenic map, it was given zone 1, means stable land. Then that Kilari area produced one fine morning a devastation. So, and the paleoseismological study by Rajendran and group, they have shown that there was a large or strong, not large, strong earthquake in Kilari some 1,000 years ago. So we don't have enough earthquake data to tell you the recurrence period of intrapet earthquakes. And I think we have not reached to that level to predict earthquakes with this data set. But we can identify the earthquake prone area like Himalaya, like Northeast India, like that. Yes.
Okay. Then another question, it's on the screen. Thank you for your nice lecture, sir. Sir, when you started working in the Kilari earthquake, what was your null hypothesis? As it was a sky earthquake and no evidence of active faulting was visible.
Kilari earthquake, we have worked for the aftershock investigation. Kilari earthquake, it occurred in 1993, and immediately we went for the aftershock investigation. So what we have presented here, I told that the main shock and aftershocks and the maximum intensity zone. So what I presented here on the Kilari earthquake is that what we understand about the typical shield earthquakes in the Kilari area or in the middle of the Indian plate. And that was the scenario, say earthquake where we have done some aftershock investigation and tried to understand the tectonics of that earthquake. So it is not the 2020 data, it is the data of 1993 aftershocks of the Kilari earthquake. So that data gave us some idea how the Kilari earthquakes occur and what was the seismic active fault, though there was no geologically mapped fault, but how our aftershock data could help us to understand the hidden fault, a south dipping active fault, and how the fault interaction model generated that earthquake and the aftershock. So that was only I wanted to share that experience.
There is another question concerning the earthquake prediction, but you already answered, I think, this. Okay, as we are much behind now,
I think yes, I have a comment here.
I think we should.
Listen, I think if you heard Professor Gupta's lecture yesterday or on the inauguration day, he has very much clarified that even if we are able to predict earthquake, suppose we say that there will be an earthquake in Delhi on January 1, what we will do? You will evacuate Delhi. So the question is, I don't think earthquake prediction is going to really, as of today, we can't predict. And I don't think that earthquake prediction will help the society. What will help the society is earthquake resilient society. We should make, as Jim clarified that, the earthquake shaking cause, minimum damage or, minimum casualties, whereas the tsunami caused the damage and the casualties. So it is not the earthquakes which kills the people, it is in the building or houses kills the people. So if you make a multi-story building on Shillong hill slope, or in Sikkim, the disaster, you are inviting the disaster. So it is not the earthquake prediction which is the flaw for the casualties. It is the buildings which is the flaw for the casualties.
Okay, thank you again, Professor Kayal. And I think we have to give the floor for the next
Thank you so much.
presentation.
Thank you. I enjoyed it. Thank you so much.
Thank you.
Yeah, well, that was a great session. Thank you, Kyle sir, for edifying lecture. Also, thank you, Rubin sir, for chairing the session.
Thank you.
Thank you all. Yes.
Heading towards the last session of the Day 3 ASSHEE 2020, we have Dr. Devajit Hazarika sir, scientist at Wadia Institute of Himalayan Geology in the Department of Geology and Geophysics. He has more than 60 journal publication in National Journal. His field of expertise is seismic anisotropy and nonlinear time series analysis and other field related in the fields of geophysics. Today, sir will be delivering lecture on receiver function analysis and its application for imagining the subsurface structure of the Earth. And I request Rajiv sir to chair the session. Over to Rajiv sir.
A very good afternoon. Am I audible to everyone? Pooja, just confirm.
Yes, sir, you're audible.
Okay. My pleasure. So, first of all, on behalf of ASSHEE, this workshop, I welcome all the participants as well as the eminent speakers and the organizers. On behalf of organizers, it's indeed a pleasure to welcome Dr. Devajit Hazarika, who is working as a scientist over Wadia Institute of Himalayan Geology, and his expertise already mentioned by Pooja. I just want to mention that his area of expertise: seismic anisotropy, nonlinear time history analysis, teleseismic receiver function study, seismotectonic study, modeling of earthquake source by wave function, seismic wave attenuation. So he has we are very much grateful for his kind presence in this session, and I believe our participants will definitely will get a broad idea about these specialized areas of geophysics, and indeed me also. So with this, I would like to welcome Dr. Hazarika to be the expert speaker for this session, and with his obviously notes as well as the time. I think time restriction is, I think that already we are 10 minutes short. No issue. I think we have to finish by 1:20. Am I right, Pooja? So with
Yes,
this, I would like to hand over the mic to Professor Dr. Hazarika for his lecture. Thank you, sir.
Thank you so much. I am audible to you?
yes, sir, you're audible. You can.
Yeah, you are audible.
Okay, just I am sharing my slides. Is it visible?
Yes, sir, it is visible.
Visible. Okay. So thank you so much. I would like to thank this organizing committee for giving me the opportunity to share my knowledge particularly with the young researchers. And I believe that most of the participants are young researchers and young scientists. So I will primarily, it will be very basic lecture on the receiver function analysis. And also I will touch a little bit of our experience in the Himalaya, its application for imaging subsurface structure. So before going to the detail about the receiver function process, I would like to talk about the general observations. First of all, why we need the passive seismological technique to explore the Earth internal structure. From the school level, we know that the major radial divisions of the Earth, that is inner core, outer core, and mantle and crust and lithosphere, all these items. So where from we got these ideas? As we know, there are several methodologies in geophysics to explore the subsurface structures. For example, we use active seismology, means we use active sources like blasting and hammering on the earth to generate the seismic waves and record it to get the informations of the subsurface. However, those informations we can obtain up to few meters or kilometers, because that much of huge energy we cannot generate. So in order to understand the Earth internal structure, we need a energy like a nuclear bomb, nuclear explosion. As in the first day, Professor Harshgupta sir told that a 6 magnitude earthquake is equivalent to a Hiroshima-Nagasaki nuclear explosion. So that type of experiment cannot be done on the Earth to get the knowledge about the internal structures. So that is why we depend on earthquake of higher magnitude earthquakes. That is, on every week we get an earthquake of magnitude 6 and above in the globe. So those earthquakes, if we record it, that give enough information about the internal structure of the Earth. I'm now here, I'm showing the Sumatra earthquake and its waveforms. These are the teleseismic waveforms. What is teleseismic earthquake? Teleseismic earthquake means the earthquakes which are recorded more than 1,000 kilometers away from the epicenter. And this left-hand side, we are seeing this is how the wavefronts spread throughout the globe, because it is a earthquake of magnitude 9. And as you remember, Professor Gupta sir's lecture, a magnitude 9 is equivalent to 30,000 Hiroshima-Nagasaki explosion. So that means it's a huge energy, and it travels throughout the body of the Earth. And these, in the right-hand side, we are showing how the wave travels and passes through different layers. And for different waves that passes through different layers has their own nomenclatures. For example, P wave, PKP wave, SKS wave, SKK wave. So all these waves that we are marking here in the waveforms are the useful informations to a seismologist. For a seismologist, we have nothing. We have only the arrival time of different seismic phases. Based on these arrival times, we do our computations to understand the internal structure of the Earth. So this is an example of teleseismic earthquake. You can see there are several phases. These are surface waves, LR, LQ, which are generated on the surface. And in the right-hand side, we are showing the different seismic phases passing through different layers of the Earth. So these nomenclatures are known to our seismologists, and each and every phases are important to study different properties of the internal structure of the Earth. If we talk about the local earthquake, this is an example of an earthquake of magnitude 5. If you talk about local earthquake, epicentral distance is very less. And all the waves that immediately travels through the granitic layer, we got, that is why we got the PG and SG phases only. But in case of teleseismic earthquake, travels through the body of the Earth, and we get a number of phases on the recorded waveforms. So this slide I am showing not to show the particle motions. It is known to, I think, all. The P wave is a longitudinal waves, S wave is a transverse wave, and surface waves, how it behaves. This I am particularly showing to demonstrate that how we relate these seismic waves with the physical properties of the propagating media. Here you are seeing the Vp equal to this much. So these are the solutions of wave equations. So we can see the Vp means velocity of P wave. It is related to density. It is related to rigidity modulus, it is related to bulk modulus. Means by knowing the arrival times of the different phases, and by knowing the velocity models, we can have the information of the propagating media. So this is the prime tool for us to study the structure of the Earth. Another thing is the measuring of earthquakes. This is one of the fundamental thing that we have to do. So this is also based on the moment of inertia, that is based on the physics principle that we know. Initially, people used seismoscopes to get the direction only, and day by day, year by year, it was progressed, and mechanical seismographs were developed. Then nowadays, in this right-hand side, we are showing these are the modern digital seismographs with a wide bandwidth and high sensitivity. So we use GPS timing for synchronizing the timing, and so these are in a nutshell about our seismic waves and the seismic instrumentations. Now I will talk about the passive seismology. Passive seismology means the study based on the earthquake data. So there are a number of techniques, passive seismological techniques are available, out of which two are very widely used for studying the structures. First of all, the seismic tomography. Seismic tomography, based on the data, there are several tomography methods. One is local earthquake tomography, teleseismic tomography, surface wave and noise tomography. So this local earthquake tomography is one of the most useful tomographic method for delineating fine features of the crust. But although these individual methods has advantages, but it has limitations also. Suppose if we want to do local earthquake tomography, then there must have local seismicity in that region, means that region should be seismically very active. But if I plan that I want to do the structure in Ladakh batholith, in Indus Tushar zone, where there is no local earthquakes are extremely less, in that case, this type of method cannot be adopted. Then we have to go for the teleseismic earthquake, means global earthquakes. So global earthquakes is very good because global earthquakes, we can go to the mantle structures. We can see the mantle gross structures of the mantle, but we cannot see the fine structures of the crust. Another disadvantage, it is not disadvantage, but limitation is that the region should have quite a good number of stations to record so as to get a good numbers of records. So sometimes in some hilly terrains, it may not be possible to establish a big network, seismological station network. Similarly, noise tomography is one of the most popular technique, and it is highly useful. It needs a continuous record in all the stations at a time. So the receiver function analysis is another technique using which, based on even one single station, we can do the study of the structures beneath the station. One single station is also possible to study the structures. So in this, before going to the details about the receiver function, ASSHEE, I would like to recollect the principles of waves, reflection, all these things we know. Now let us consider a P wave is incident on a velocity discontinuity. Then what happens? Reflection will happen. That will happen. P wave will be refracted as a P wave, but in some particular angle, P wave will be converted to S wave. P wave is longitudinal, S wave is transverse. Okay. So this phenomena we use in the receiver function analysis. When in velocity discontinuity, P wave converts to S wave. Since there is a difference in velocities, and we know that this S wave has originated in the discontinuity, so it provides a clue to find the crustal or any other depth of the converting layer. Not only P wave converts to S wave, similarly S wave also converts to P wave. Then in that case, we call it S2P receiver function. Okay, so in S2P receiver function, we take the waves that converts from S wave to P wave. Now, let us know what is the receiver function. So receiver function is nothing but it is a time series which shows the response of the earth structure. Now we know that what is a waveform of an earthquake. It is a time domain, it is amplitude versus time, and it is comprised of the source effect, path effect, and earth response. Now here I am showing P wave part of an teleseismic earthquake, where you are seeing that the first onset of the P wave is very clear. However, after that, in the tail part, lot of complex waveforms are visible. Now, if we know that it is a complex multiplication of source, path, and earth responses, so if we divide the radial component of the three-dimensional waveform, radial component, if we divide it by vertical component, then most of the things, for example, the instrument response, because the instrument is same, so it will be nullified, source will be nullified, and path will, same path it is traveling, so path effects will be nullified. Only what will remain? The ratio of the horizontal earth response and vertical earth response will remain. That is called receiver function. So if you divide tangential, then it will be known as tangential receiver function. So just below these waveforms, I am showing the computed receiver functions. This division, we call it deconvolution. So if we deconvolve the vertical component by the radial component by vertical component, so we see that this PP means direct P phase and P2S converted phase at the discontinuity is very clearly visible, whereas the noisy part, which is contaminated by source effect and path effect, will go. And we'll get only the converted phases and corresponding reverberations. Here we are showing the ray diagram, incident wave, how it is incidented. Then these are this is the direct P phase, PS, P2S converted phase, and these are the crustal reverberations. So this converted phase and the reverberations provides important constraint, because you know that PS phase is lower than direct P phase. So this time difference between the two, and if we know the velocity, then we can get the depth of the discontinuity. This is the basic principle of receiver function. So as I told in the beginning, this is for beginners and research scholars. So I am giving emphasis on each and every step, how to do, how to proceed. First and foremost is data selection. Then next is rotation, filtering, and deconvolution. Deconvolution that I have already mentioned are one of the most important steps in the computation of receiver functions. Then few standard approaches like move-out correction and stacking of receiver functions and inversion is important to get the final result outcome from the computed receiver functions. We always select data from minimum should be 5.5 so that the energy of the earthquake will be such that it can travel throughout the body of the earth. So preferably 6 magnitude earthquake is better for receiver function analysis. Earthquake should be teleseismic, means epicentral distance should be 3000 to 9000 degrees. Why it is so? Because if we consider epicentral distance is very small, then wave will directly come and the incident angle will be horizontal. In that case, conversion from P to PS will not be possible. And if we take larger epicentral distance, then it will take a curvature path and it will reach the station and incident angle will be almost vertical. In that case also, P to PS is not possible. So that is why we select a particular epicenter distance for this study. This is also one of the most basic thing, but still we should know what is azimuth and what is back azimuth. If we are standing on the station, then draw a line to the north and draw a line to the epicenter. Then positive angle is called back azimuth. And similarly, if we stand on the epicenter, draw a line to the north and draw a line to the recording station, the positive angle, red color, is azimuth. So now, because we install the seismometer, this is the seismometer, we install the seismometer in geographical north and geographical east, and this seismometer comprises of 3 perpendicular, initially perpendicular pendulum. Now, if earthquake can come from any direction, to get the highest energy in the radial component, practically we should fix the sensor in the radial direction, but which is not possible because earthquake has already been recorded. So in such case, what we do, we rotate the seismogram following this equation. This is north and east component of the waveform can be converted to radial and transverse by rotating the signal. So this rotation is one of the major component in receiver function. Another issue is filtering. Filtering, because nowadays the broadband seismographs, they record a wide band of frequencies, very high frequencies, even up to the 50 hertz in 100 samples per second can be recorded. So in such case, for our study, we do not want such high frequency noises. So we use the Gaussian filter. This is the expression for the Gaussian filter, which is controlled by the Gaussian parameter A. So we can design different filters as per our wish. Now, what is the importance of filter? It is very simple. From here we can see the velocity equal to frequency into wavelength. So minimum resolvable length or resolvable length of the discontinuity can be obtained by lambda by 4. For example, if you consider Gaussian parameter 1.5, the corresponding frequency will be 0.6. Then in that case, if we consider the velocity of S wave, because we have to consider S wave because P2S converted phase is a S wave. So if we consider velocity of S wave in the crust 3.7, then your lambda will be 6 kilometer. So minimum resolvable length will be 1.54. That means your resolution will be poor if you take the frequency low. If you take higher frequency, you can go for the finer structures, but there is a limitations. You cannot take too much high frequencies because that will create the problem related to the scattering and other effects. So we have to find the optimum filter for particular discontinuity. If you go to the crustal Mohorovic discontinuity, then filter will be different. And if you go for the 440 and 660 kilometer global discontinuities, then we go for the lower frequencies. This is, as I told, that the convolution is one of the most important part of the receiver function computation. And as I told that this is there are several number of the convolution processes, but I'm showing here two, which is very commonly used. One is water level deconvolution, and other is iterative time domain deconvolution. So in water level deconvolution, it is very simplest to understand. The time domain waveforms will be converted to frequency domain with the help of the Fourier transformations. Then in time frequency domain, deconvolution is simple to understand. It is simple division, and then after dividing radial by vertical, again it will be inverse Fourier transformations will be done to get the waveform, which is nothing but your receiver function. But while dividing, there is an issue. If something is divided by a very small number, then there is a problem in the computation. So we fix a level that is called water level, and we remove the minimum frequencies below this level, and after that we divide. So this is the water level deconvolution. In my studies, I have used this iterative time domain deconvolution, and this method is a least square minimization method. It follows a least square minimization of the difference between the observed and horizontal seismogram and predicted signal generated by convolution of a iteratively updated tree with corresponding vertical component seismogram. So I recommend to read the Kikuchi, Kanamori, and Ligoria and among those who are interested for computing receiver functions for details. Now, if we keep a station for 2 years and 3 years, we will quite a good amount of data we can record. This global earthquake data, teleseismic data of magnitude 5.5 and above. These are the examples of receiver functions at 2 stations I am showing. This stations is located over the Indo-Gangetic plain, and there is this formation of doublet in the beginning is a characteristic feature which indicates the presence of sediments at the top of the layer. And this is P2S converted phase at the depth of Mo. Similarly, we are getting here one mid-crustal layer, and then the Mohorovic discontinuity. Now, these are the examples. These are the normal processes in geophysics that correction of move out correction is very much important, because the earthquakes are arriving from different epicentral distances, so slowness of different waveforms are different. So in order to stack, because we do the stacking of all the receiver functions before doing the modeling. So in that case, to enhance the PS phase, we have to get a coherent PS phase, for which we have to do the move-out correction. So I will not go in details about this. This is a general geophysical method. Now, what for we are computing receiver functions? We would like to know the thickness of the converting layer. We would like to know the properties of the converting layer. So in that case, before going to do the modeling and other thing, we do the ASSHEE stacking method. This is a very commonly used method. This is the direct converted phase T1. T2 and T3 are the multiples. These arrival times of these three direct phases and multiples can be expressed by these equations. I will tell where from these equations have arrived. Now, if you want to solve these three equations, then we have to consider different values of H, different values of VP by VS ratio, and slowness P. So in that case, if we draw three lines, we'll get a common intersecting. So this point is nothing but your corresponding crustal thickness and VP by VS ratio. VP by VS ratio is very much important because it is directly linked to Poisson ratio of the crust, if we talk about the crust. So this analysis is a standard tool nowadays. So this we do prior to the receiver function inversion. As I told you, the way from these equations have come, you can simply just see that time is nothing but distance divided by velocity. So this dz by vs means it is the velocity, it is time of the s, this is time of the p, so this is p and s time difference. Now, as we know that reciprocal of the velocity, this is the slowness in the direction of propagation, and p is the horizontal slowness, then we can easily calculate the vertical slowness based on the Pythagoras theorem. So if you put these values, the equation becomes Tp equal to this one that you are getting here. So you can see this is very basic that I am telling. Then the final outcome is that we want to know the velocities structure beneath the S recording station. For that, what do we do? We relate the receiver function, stacked receiver function, with a velocity model. How we can do that? For that, we assume a initial velocity model that has been published by some other research, or that may be a nearby published result, or maybe ISP velocity model, which we are considering as M1. And M is suppose the actual model that you are going to have, and dm is the correction factor. In that case, if z represents the partial derivative of receiver functions, then z dm equal to d. So this can be rewrite. It's very simple. You can go to the M1 at 1990. All details has been given there. So Zm equal to d plus Zm naught. This is the equation that we have to solve to get a required velocity model M. How we do that? I will simplify this. We use a singular value decomposition method to compute the matrix inverse and solve the inverse problem. First, what we do? We stack the receiver functions in different back azimuths, and we consider the initial velocity model, and based on the Monte Carlo technique, which has been explained in the M1 until 1990, we perturb the velocity model into several thousand velocity model, like 40,000, 50,000. These are the velocity model. This is the depth, and these are the velocities. So quite a huge number of velocity model bounded by the red lines we generate, and we compute synthetic for each and every velocity models, perturbed velocity models. And these particular bunches we have selected, which matches with the observed receiver function. This is the standard deviation bound, the gray color, after stacking the receiver functions. So then this process, we choose out of this model, we choose one velocity model, and take it as an initial model and repeat the process until we get a good matching. So this is one of the methods, but this method has some limitations. It considers fixed Poisson ratio. So we did our next inversions using the neighborhood algorithm. This is a very popular algorithm, and this is a class of global search approach that is fully nonlinear and derivative-free direct search technique. So for this, I will refer this Ambridge 1999 for details about this process. And in order to see the receiver function image in a profile, we do the common conversion point stacking. This is a geophysical technique in which we imagine some 1 kilometer by 1 kilometer or 2 kilometer by 2 kilometer area through which how many waveforms from different stations has pierced. And we stack it and we get the image, we construct an image like this. This is the TCP image, one example I'm showing. It is from a published literature. We'll show our results also. So they are creating the image up to 200 kilometers, but we can go much deeper, like we can study the 410 kilometer global discontinuity and 660 kilometer discontinuities. So these are the basic things that just I am showing for the interest of the young researchers, and some links also I am giving for to get the literatures and quotes. The iterative deconvolution quotes, those things are available, freely available. Now, I will stop the basic things here. I have just given a glimpse for the receiver function process. Now I will go to some studies that we have carried out in the Himalaya. So this is the instrumentations. The triangles represents the seismological stations. Few of them are campaign board stations. Now in Wadia Institute, we have other networks, newly established networks also, which are not shown here. So these are the equipments that we are using here. I will study this profile-wise. This one, Satluj Valley, 2, Garhwal Himalaya, Kumaon Himalaya in Kali River Valley, and third one is Ladakh, Karakoram zone. Now, before planning for an experiment, we should have a motivation. So what is the motivation behind this receiver function analysis for imaging crustal structure in the Himalaya? First of all, the variation of seismicity along the strike of the Himalayan arc. If you see from the eastern Himalaya to the western Himalaya, the blue dots shows the seismicity from 1960 to 2012. If you see, it is published by Gehlot and Kundu and Arora at 2012. If you see, there is a huge differences in seismicity distribution, and usual concept is that due to the Indian place is under thrusting beneath the Himalaya, and this Himalayan wedge has been developed, and this several thrust hits, Himalayan frontal thrust, main boundary thrust, main central thrust, all these thrust hits, they are dipping towards north, and it touches a common interface, which is the boundary of the Indian silt rocks and the Himalayan wedge. So this is called seismogenic. This is called the detachment surface or decolema, or also it is called main Himalayan thrust. So all the energy accumulated due to the India-Asia collision is accumulated in the main Himalayan thrust, and sometimes it comes out in the form of the earthquakes time to time. So as we know, this region is very much active, the northwest part of the Himalaya. If you see the seismicity, if we zoom out this portion, you see only the blue color. Blue color means it is earthquake of magnitude 5 and above. So one thing is very much clear, that this is the similar region of northwest Himalaya. In this particular, this is Kori Changro normal fault, which is very much active region. So it is quite contrasting that this is Himalayan seismic belt straddling the MCT, both sides of the MCT. Normally, usually we get earthquakes in both sides of the MCT. However, in this particular segment, we do not get earthquake of magnitude 5 and above. The frequency is very less. And this epicentral plot is from 1960 to 2020. So in such case, we have definitely a curiosity. Why is there any difference in structures, or is there anything because of which there is no earthquake, or why the earthquake has been shifted to the north? So for that, these are the scientific questions. That is there any role of the main Himalayan thrust? Because several literature says that main Himalayan thrust has a ram structure beneath the main central thrust. So that may create earthquakes. And our curiosity is that is there any ram structure beneath this region? And whether is there any intercrustal low velocity zone, because presence of fluid and partial melt creates a low velocity zone. And is there any such low velocity zone? So we have designed an experiment and we tried to get the receiver function image for the Satluj Valley. So I am not showing the intermediate receiver functions and other things. I'm directly coming to the image. And here we see that these yellow circles, these are the results coming out from the inversion. These are the main Himalayan thrust, the step jump in the main Himalayan thrust. And these black dots are the Mohorovic discontinuity. The red color also shows it is quite coincident with the CCP image. So here we see that there is no such strong ram structure beneath the MCT. Whereas if you see in the Garhwal Himalaya, where there is a clustered seismicity, Cadwell et al. In 2013, they reported a ram structure in the main Himalayan thrust. So this study emphasized that there is a strong linkage between the ramp structure in the MST and the seismicity. Where there is a ramp structure, there is a seismicity. And here the ramp structure is not there, so there is no seismicity of magnitude 5 and above is observed in this region. The seismicity to the north has a different cause. It is not related to the MST, it is related to the Korichango northern fault. So these are the observations that I already have told about the thickness and about the ram structures, and we observed the sedimentary column 3 to 4 kilometer in the Indo-Gangetic plain. So these are summary. So this work has been published in Journal of Geophysical Research, Solid Earth, in 2017. Now I will go to the Kumaon Himalaya. This pink color line we have already explained. This red color is published by Cadwell et al., where they observed a sharp ram structure beneath the MCT. And this is another experiment that I am going to show you. This is Kali River Valley, where we have established where we have established 15 seismological stations in 2016, and still this network is working. So this region is very much interesting. If you see the geology in the map, that it is a huge clippe structures. Almora clippe is here. Then Siplakot crystalline belt is here, which is a geologically also it is reported that there is a duplex structure in the Siplakot crystalline belt, and large part is occupied by the lesser Himalaya. So the receiver function image that we have observed in the Kali River Valley, say it can be observed that the crust is comparatively thinner compared to the other part of the northwest Himalaya. It is starting from 38 kilometer and maximum 41 kilometer beneath the Siplakot crystalline belt. Another important feature is ram structure in the MST has been observed from the CCP image. The dotted line shows the MST interpreted based on geological cross-section studied by Srivastava and Mitra. So it is quite well matching with the geological balance cross-section. Besides this, we observed the lower crustal low velocity zone and a little bit of upper crustal low velocity zone. And the ramp is almost 20 degrees. So we have superimposed the velocity models obtained from inversions, and it is observed a trough in velocities beneath the in the region where we are observing the low velocity zone. And as I have shown in the nearest neighborhood method, it provides the Poisson ratio variations with depth. And if we see closely, the Poisson ratio is very high where we are observing low velocity zone. So this lower crustal low velocity zone in the Chipplacoot crystalline belt is caused by, as per our inference, is caused by shear rating in the ductile regime, and or maybe the decompression and cooling associated with the exhumission of the Chipplacoot crystalline belt. So this red, this blue dotted line shows another profile, another experiment carried out by Zhu et al. In 2017, and we have compared and observed, and it is almost quite continuous. There is a gap of about 50 kilometers, and if we see, they have also reported the MOHO up to 80 kilometers. That means the MOHO, it starts at 38 kilometers, goes up to 42 kilometers, and then it goes up to 50 kilometers, and then up to 80 kilometers. So it is suggested the underthrusting of the Indian plate. Then they also observed low velocity zones. So this is in a nutshell about this experiment. We have also carried out the seismotectonic study in the region, Kumaon Himalaya, where we have just now shown the image. And it is observed that seismicity is clustered above the ramp and the low velocity zone in the upper crust. The cluster seismicity coincides with the ramp, which is critically stressed. The diffuse area of seismicity is interpreted as the lesser Himalayan duplex structures. These are the nodal planes projected in that particular AB axis, and it shows that the implicate thrust rates of the duplex. So this paper has been communicated to tectonics. So fluid and seismicity linkage has also been reported by the other magnetotelluric experiment. This is the image by the magnetotelluric experiment in the Garhwal Himalaya. So there is a strong linkage between presence of fluid and the seismicity. This is done by our institute, Rawat et al. 2014 in tectonophysics. So this is the second experiment I have demonstrated what we have done, and one more because the time is still there, so I can go for another interesting observation that we have done in the Ladakh Karakoram zone. As we all know, that Indus Changpo Susar we can cross only through this Ladakh Karakoram zone, because this corridor is accessible for us, and this region is very much interesting, as we know that Indus Susar zone is the surface collision boundary of the Indian plate and the Eurasian plate. And this is the Sumurari Dome, which is in the Indian affinity, and this is Ladakh batholith, which is in the Asian affinity. This is Karakoram Fall Zone. As we know, the Karakoram Fall Zone is a huge fall, which is a textile strike slip fall reported by different studies. And the tectonic setting of the region is distinctive because of these oceanic subduction, remnants of oceanic subduction is still visible. And this ophiolitic suit, the Nidar ophiolitic complex, is sandwiched between the Sumurari ultra high pressure USP rocks of the Sumurari crystallines and the Ladakh magnetic arc. So this region we have recorded quite a good number of teleseismic earthquakes, and we have applied the receiver function analysis that I have already explained. One interesting observations. So if you closely observe, these points are nothing but the ray piercing points. The triangles are our stations. So what is the ray piercing point? The piercing points plotted at the depth of Mohorovic discontinuity. When waves comes, it pierces at different angles at the Mohorovic discontinuity. So these are the points at the depth of Moho discontinuity. So now, why we are showing, because these white points, which are the piercing points beneath the nidorophyletic complex in Indus-Ushar zone, it is observed that when the waves pierce the region through southeast, it pierces the region of the nidorophyletic complex and the Indus-Ushar zone, and it doesn't show Moho discontinuity clearly. It is Moho is diffused, whereas from northeast direction and northwest, it is very much clear. So this suggests a quite complex structure and azimuthally varying structure in the Ladakh-Karakoram zone. So this is the image that we have observed in the Ladakh-Karakoram zone. We have identified that Moho starts from about 55 km in the Tatin Himalaya or 60 km in the Tatin Himalaya, and it goes up to the 80 km beneath the Ladakh-Karakoram zone. Besides the Moho discontinuity shown by the yellow line, we are getting another very prominent phase like Moho in the forearc region of the Ladakh-Karakoram zone. This we have interpreted as closized Indian continental crust. We have compared our velocity models with the magnetocaloric experiment carried out by Arora et al. 2007, and it is quite well matched. The low velocity zone and low resistive, high resistive zone are matching well. We have also identified low velocity zone beneath the Ladakh-Karakoram zone, which is maybe because of the intercrustal low velocity zone we have observed at 15 to 40 km, extending from Tatin Himalaya to the Karakoram fault zone. And this may be, we have interpreted as the partial melt at the mid-crustal depth. So these are the summary of these experiment. So I have shown 3 experiments that we have done, but we have done several other studies in the Eastern Himalayan syntaxes, in the Luhit Valley, and in the Siam Valley. But I think due to time limit, I will stop here. And particularly the students, they can ask about the process and procedure. And thank you very much for your patience for this technical talk. I would like to acknowledge my director of our institute and my students and colleagues for their contributions in these 3 experiments. Thank you so much, and I'm thankful to the organizer for giving me the opportunity to present, share my experience.
Yeah, thank you, Dr. Hajarika, for your illustrative presentation with the basics of geophysics, which will help the participants and the new researcher in this field. And obviously, the case studies you have shown, obviously, it is being well noted for the society as well as for the researchers. It's a very nice presentation. Now it's a time for this platform is for question and answer. Few question and answer we can expect from the audiences. So please, one question has come from Abhishek Sharma. I think you can read it.
In Abhishek Sharma, in inverse modeling process, how can we get non-invertible kernel matrix if we are constrained not to use the damping parameters method for inversion? Because the inversion process that I have explained, it is based on it is a nonlinear inversion process. The first one that I have explained, it is a nonlinear inversion process. It has some limitations, but the neighborhood algorithm, it is a kind of genetic algorithm where the of Voronoi cell is adopted. So we considered a 24-dimensional space based on the shear velocity, Poisson ratio, density, and parameters. So and then this 24-dimensional space, the space will be divided into several Voronoi cells, and accordingly, the synthetics will be generated for each and every small cells. So this is the basic concept of the nearest neighborhood modeling technique. And I think I'm not very much expert to tell about the detail about the technique. I prefer that you go through the Sambries et al. 1999 for detail about the nearest neighborhood modeling method for receiver function inversion.
I think the next question is from Gautami. Sir, can you see the
Yeah, I can read it.
question?
Yes. Fluids and partial melting is the reason for low velocity layers in crust. But what is the mechanism behind this type of fluids in the crust? The main mechanism for getting fluids or generation of the fluids in crust is number one, in the upper crust, it is due to the underthrusting of the sedimentary rocks and the this water content of the underthrusting sedimentary rock is one. And if we talk about the lower crust, it is particularly due to the shear heating. Shear heating is one of the major cause. And in case of Chiplakot crystalline belt, we are talking about the decompressional belting that can be also a cause of observation of the partial melt. Yeah, another question I saw in the screen, that is receiver function inversion is always nonlinear and on non-uniqueness. How much accuracy is there in the final model of inversion? Which method you are mostly recommending? I recommend mostly the nearest neighborhood algorithm. This algorithm is a type of genetic algorithm and it reduces a lot about the nonlinearity and non-uniqueness problem. And if you talk about the accuracy, as I told in the frequency selection, if you take a lower frequency, then you have the limitation in the wavelength itself. You can get the idea you do not have the resolution of 1.5 kilometer plus minus in receiver function. If you go to higher frequency, then it will come down to half kilometer plus minus. But you cannot go beyond very higher frequency because it will be contaminated with the scattering and other geometrical spreading and other effects. So there are limitations in the method, but for geodynamic study to get the idea about the departmental discontinuities, Mohorovic discontinuities, and intracrustal features, maybe 0.5 kilometer is fine. Yes, please.
May I ask a question? If there is any information about gravity anomalies there, I mean, if you find some correlation between, if it's available, between the gravity anomalies and the boundaries which you are finding using seismological
that is very
methods.
supportive for receiver function study. We have one study in Northwest Himalaya that we use for preparing our results, which is also coming very close in Northwest Himalaya. But we have very less study in the northwest part of the Himalaya. It is obviously it is very good if we have the gravity study and if we can compare with the receiver function. It is always better, and I prefer to compare the results of our receiver function image with magnetotelluric experiments and also the gravity study if it is available. But yes, it is very good if we can compare both.
Thank you.
So, thank you, sir, for your nice, discussion and suggestion as well. So obviously, we are benefited from your presentation as well as the answer, that means questionnaires. And obviously, I believe this platform will give a chance to communicate you as when we require have some queries. So with this, on behalf of the organizing committee, so once again, thank you, and as well as the participants, as well as the experts from our country, as well as from the all around the world. So it's my pleasure also to session this chair. Pooja, thank you.
Yeah, welcome, sir. Thank you, Devajit, sir, for your wonderful session. Sir, I request you to take up one question for the participants for a quiz session.
Okay. So, because I was originally, I did research in Northeast India, so I want to quickly ask one question. Can you name one gigantic strike slip fall in Northeast India?
Okay, this is a question for our participants. We give you 1 minute time. You can drop your answers in the comment section. Please drop a question. Please drop an answer along with your email IDs. Okay, time's up. And we will check with the answer. Thank you so much, sir, for the wonderful session. It was nice having you here for ASSHEE 2020.
Thank you so much.
Thank you
And
once again.
I request the young researchers, they can communicate to me for any technical help regarding this particular methodology. Thank you so
Sure,
much.
sir. Thank you so much. Thank you once again. Thank you, sir, for chairing the session. Thank you, Rajiv, sir. And now I request Kyle, sir, to take up one question from your session. As we couldn't take it that time, we were running short of time. Can you please take up one question from your session,
Yes,
sir?
I think that question was already asked by Dr. Devajit Hajarika. I thought that he is asking the question from my session. He has done the job already. And did you get any answer? He asked a
Yes, sir.
gigantic
We are
call.
getting answer in the comment section. We
Okay,
will check with the answer and we'll announce the winners in the tomorrow's session.
Actually, the question was not heard by many of our participants. So, can we repeat the question? Everyone is asking about repeating the question.
So, can we have one more question from your end?
From you mean from my portion?
Yes, sir.
Okay.
Yes,
Okay.
sir. One more question from you.
Okay. Can you tell me what type of fall mechanism you expect in the known rift basins of peninsular India, say in the Kast rift basin or in the Narmada rift basin? What type of mechanisms for earthquakes you would expect and why?
Thank you, sir. Thank you for the question. I think our participants are knowing the question and you can just drop your answers in the comment section now. We'll be giving you 1 minute time to drop an answer.
Okay.
And we will check with the comment section and we'll announce the winners in the tomorrow's session.
Okay. Thank you so much.
Thank you, sir. We can wind up today's session. Thank you, everyone, for your precious time.
Thank you so much.
Thank you, everyone.
Thank you. Thank you, Devajit. You have done a wonderful job. And Ruben, Vera.
I got inspiration for you for the students. I have to prepare, so I'm preparing. For
Let me share one minute. Devajit is one of the brightest and youngest scientists in our country, and he started his receiver function. You can say training or his first interaction with one of the greatest professor of Russia, Professor Venik. Devajit came with me in Russia sometime in 2006 or what time? Devajit in 2006?
Maybe 11, 12.
11. So sometime in 2011, Devajit accompanied me to Russia on our DST Arabia project. And he told me, "Sir, I want to interact with Professor Venik. You give me some time for that." And he interacted with Professor Venik. And that was his starting point to learn receiver function. He was a man of, tectonics and anisotropy and Kodaw and all these things. He started his receiver function knowledge or say training or motivation from Professor Venik, the scholar of Russian scientist. And today, he is, I think, in my assessment, he is one of the best receiver function seismologists in the country. And you gave a wonderful lecture. And I suppose the young researchers who are in this field, who are working, They have got enough, knowledge and experience from you, and they will definitely interact with you. So we are really, on behalf of the organizing committee, we really thank you so much for sharing this tremendous knowledge and experience on the Himalayan receiver function results. Thank you so much. Thank you.
Thank you so much, sir. Thank you.
So thank you, everyone. Let's conclude day 3 of ASSHEE 2020. Thank you once again. See you all tomorrow.
Thank
See
you.
you. Bye.
Bye-bye.
The ASSHEE International Workshop was formulated in 2019 by NIT Agartala through an international collaboration with Russia, Finland, and Italy. It achieved an overwhelming success from the students, young scientists, engineers, and professionals, not only in Asiatic countries, Asian countries, and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy, and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise, and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering, and seismic hazard mitigation.